So I will welcome everyone to the tutorial on fog computing for industrial IoT that was organized by myself, Alessandro Papadopoulos from Lund University, and by Wilfried Steiner from TT Tech in Austria. So the program of this tutorial is as follows. So initially, we are going to have an introduction to some fog computing and industrial use cases and open issues from Wilfried Steiner. That will be the first speaker. And as I mentioned, this will not be recorded. So I will pause the recording there. And after that, we are going to have the presentation by Karl-Erik Årzén from Lund University that is focusing on control over the cloud, over the edge cloud, sorry. Then we are going to have a short break of 15 minutes just to stretch our legs to be prepared for the third speaker, that is Professor Ivona Brandic from TU Vienna. And finally, oh, there is it seems that the screen is too large. I cannot see the whole page of slides. Oh, wait. Do you see it better right now? I'm trying to.
I don't have the issue. Maybe the person.
I also see everything, so I don't know.
I see everything.
Okay. Perfect. Okay, but finally we are having not finally, we are having Ivona Brandic that is focusing on data-driven techniques for fault tolerance in edge computing, and this is going to be a 1-hour lecture. And right after the long break, we are going to have a much longer hands-on session on some more practical aspects of what Ivona will present. And this last session is going to be given by Atakan Aral from University of Vienna. And I will just make some closing remarks. So I report here the schedule in Central European time. Okay, I think we're good. Sorry. So I want to hand over the word to Wilfried Steiner with the first presentation. I will stop sharing and I will stop now the recording.
Okay, thank you. My name is Karl-Erik Årzén from Lund University, and the title of this presentation is Control over the Edge Cloud, Possibilities and Challenges. And it is joint work with two of my colleagues, Per Skarin and Maria Schiel. And Per Skarin, he is an industrial PhD student working normally for Ericsson Research. And most of what I talk about today is from his forthcoming PhD thesis that will be out in December this year. Okay. So, the cloud. As soon as you use any laptop or phone or something today, the likelihood that the computations will be performed in a data center somewhere is very, very large. I mean, it doesn't really matter what you do, personally, so to say. Music, television, buying things, books, and so on. So it's executed in a data center somewhere where electricity is cheap and where there is a cold climate. And this is all well. But what about mission critical applications, safety critical applications, the applications you have typically in robotics and industrial automation, where you have requirements on low latency and good performance? And also, in this case, we assume that you want to have a wireless connectivity between the plant and the controller. These are not deployed in the cloud today. Why is that? Well, if you use 4G or LTE, the radio latency is too long. If you use 5G, when that becomes available, you have a shorter radio latency, down to 1 to 5 milliseconds, so that's good. But typically, the large portion of the delay doesn't come from the radio interface. It comes from the communication between the base station and the data center. Another reason is that the whole cloud ID is based on best effort and utility computing. So there are no performance guarantees whatsoever. And then, of course, we have security issues. I won't talk about those at all today, but they are very important. So what should you do about it? Well, as I said, 5G gives you a little bit, but not enough. The delay from the base station to the data center, well, the recipe is, of course, then to put the computations closer to the plant, closer to the base stations, closer to the edge. And when I say edge, since I'm collaborating a lot with the telecom community, I mean the network edge. So it's not a device edge, it's a network edge. So typically nearby the base stations. And what about this thing about having no performance guarantees? Well, then you need to develop more real-time-ish cloud systems, and you need better resource management techniques. And that is something which I won't discuss at all today either. Okay, so edge clouds then. Yeah, that's nice. We have local data centers at the network edge, typically connected to base stations. They can be in office buildings, in factories, they can be in sports arenas and things like that. But we don't only have either the data center far away or the local edge node. We can also have nodes in between, building a fog, we can say, of computation. So that's the fogged cloud idea. However, if you talk to people in the communications community, they often don't use fog cloud that much. They typically, at Ericsson, they call it the network compute fabric or the network computing continuum. So that's essentially alternative names for this, where you have the possibility to do computations essentially anywhere in your network. And this is, of course, driven by the requirements from third-party applications like control applications, but it is also driven by the needs of the network itself. There is a strong trend towards cloudification of the base stations and the computations. You have cloud radio access networks and so on. And then the computations are implemented in terms of network functions or chains or meshes of network functions. And these you want to have virtualized. So that's another push towards this technology with edge fogs or network compute fabrics. So control over the cloud, what are the possibilities and challenges? Well, we have this illusion of infinite compute resources because, of course, it's only an illusion. They are not infinite and they are not for free. You pay depending on how much you use and so on. But still, if we assume that they are infinite, they open up new ways of doing control. You don't have to do it the old ways. But then we have the challenges. Even if we use 5G or 6G or whatever, as soon as we have wireless connectivity between the plant and the controller, there is always a risk of losing the connectivity. And this, of course, can be ever so small, but it's still there. So that means that you need some type of local backup strategy, close to the plant, close to the device. So that's one challenge. The other challenge is the large variation in time delays. Coming from the radio, of course, but that's not the main part. They come from the delay between base station and data centers or edge nodes, but they also come from the cloud infrastructure itself. I mean, accessing all these cloud services takes time. It's not for free. And then finally, the control computations. And depending on what type of controller you implement, this can be very small, but it can also be substantially large. That means that you have to have some approach to handling this. You can use some type of advanced delay compensation, or you can use buffering. And buffering is what we are using here today. And then, of course, also the security privacy issue, which I won't discuss today, but it is important. But it's not our field, so to say. Okay, control over the cloud. The idea is that some parts of the control loop should execute in the cloud. And what should then be in the cloud? Well, it should be something that requires a substantial amount of computation, I think. I mean, there is not much point in putting the PLCs or the PID control in the cloud because it's so cheap to implement using ordinary techniques. Of course, machine learning based control. If you use reinforcement learning or deep reinforcement learning, which is another way of saying that you are doing dynamic programming, then of course the cloud can give you a lot. But it can also give you a lot if you use optimization-based control techniques, and that is what we are focusing on in terms of so-called model predictive control, MPC, which is a technology that is used widely in the industrial automation community today already, but not in the cloud. Okay, so model predictive control, you have your plant, you measure your outputs or your states, you send them to an optimization program, an optimizer, where the optimization problem is formulated so that you want to minimize some cost function, some quadratic cost function in the states of the plant and in the control signal of the plant. And here we have these two weighting matrices Q and R that tells us how much we should weight the state against the control signal. So this we initialize with the current state, either measured or obtained from an estimator. Then we have an equality constraint that is the plant model. So this is the model of the plant that we are controlling. In this case, it's a linear model, doesn't have to be. Then we have constraints either on the state or on the control signal. And in this case, they have been formulated as hard constraints, meaning that you have to meet them, but they can also be formulated as soft constraints, and in that case they are included in the cost function here, and then you might violate them, but not too much. So you solve this optimization problem, and out comes a sequence of control signal, the one that you should apply now, the one that you should apply next time, and so on and so forth, up until the prediction horizon that is given by this N. So you have this horizon of control signals, but you only use the first one. You send the first one to your actuators and to the plant, and then you do the same thing all over again next sampling instant. You measure the output and the plant state, send it up, you solve an optimization problem, you get this sequence of control signals, you send it back, you only use the first one, etc., etc. And of course, depending on the type of process you have and the type of constraints you have, solving this optimization problem can be quite time consuming. And it's not always so that you obtain a solution, because if you have hard constraints, it could be that you cannot find a solution that meets the constraints. And in that case, you say that the system doesn't allow a feasible solution. Okay, so what are now the different research directions that you can take? Well, one approach, of course, is to try to make the cloud more predictive, more real-time-ish in nature, typically using network edge data centers and private 5G networks. Try to make the OS more real-time, the hypervisors, the virtual machines, the containers, and so on, and the real-time networks, for instance, TSN. So that's one way of doing it, and that's a very natural way of doing it. But there is actually another way of doing it, and that is to try to design the controller in such a way that it is robust to or can adapt to the cloud-induced uncertainties, typically in latency. And we call that resilient cloud control. And that is the topic of this talk. And the idea behind this is that you shouldn't really need to have some kind of special real-time edge or real-time cloud. You should be able to make use of conventional clouds and conventional cloud software stacks. So it should be very easy to develop and deploy these types of systems. And the real, so to say, burden you put on the controller. It is the controller that should react and adapt. When you talk about cloud computing, traditionally, we divide things into infrastructure as a service, platform as a service, and software as a service. But today, if you go out in industry in practice and look upon what people are using, you have, of course, the virtual machine-based solutions, typically using OpenStack. You have a lot of container-based solutions using Dockers and Kubernetes and maybe mobile. And then you have also increasingly often have function as a service. Serverless computations, which is a stupid name because of course you have servers, but you don't have to bother about the service yourself. So functions are coming more and more. If we look upon the delays that you obtain here, here is an example where we have used a lot of different protocols and software elements in order to implement things. And we have in red, where we use a remote public data center. It's an Amazon data center in Germany, I believe. In orange yellow, we have a local data center. You can call it a private data center, but that is very close to the plant that we are controlling. And here we have to the left, the very low numbers here. They are, so to say, the ideal numbers which we obtain, assuming that we have speed of light type computations. And then if we go up here, we have, so to say, added one layer of the software stack and protocols. And then if we go further up, we have added more layers of the software stack. And typically, the largest delays we get if we use function as a service with Lambda. And that's, I mean, that's also what we typically would like to use, because it is very easy for the developer and the deployer to use this. So the question is this: can we develop the control system in such a way that we still can use function as a service and still get things to work? And that is what we are looking upon. So the architecture, since we have this risk of losing connectivity, we need a backup controller. If the request to the MPC calculations in the cloud does not generate the response. And there can be several reasons for this. It can be a too long communication delay, too long computation delay. It can take too long time to access the cloud. And it can be that the optimization fails to generate a feasible solution that meets the constraints. So we have our client, and we have some backup controller here, which in this case is a so-called linear quadratic controller. And then we have this MPC node that simply sends away requests to the cloud, either to the data center or to the edge where the optimization is performed. So what type of backup controller should you have? Well, it's very natural to have a LQG controller, which you can interpret as an infinite horizon MPC controller. It uses the same type of quadratic cost functions as the MPC, but the horizon, the N, is infinite, and it doesn't support handling of constraints on the state and control signal. The nice thing with this is that there is an analytical solution. That means that you don't have to solve any time-consuming optimization problem. And the nature of this controller is state feedback, so it's very cheap to implement, not a lot of computations. So that's one way of doing it. Another way of doing it is to use an MPC controller also in the device, but an MPC controller that runs at a slower rate. For instance, you can run it at twice the sampling period of the cloud MPC. And that actually gives you twice as much time to solve the optimization problem. And the optimization problem is half as large if you have the same prediction horizon expressed in seconds. So that's a kind of a win-win situation. And this is motivated by the fact that if you use the typical rules of thumb for selecting your sampling period, these often are expressed as in such a way that they return an interval, often a quite long interval, as allowable sampling periods. So somewhere in this interval, that it can be between 2 to 4 times, it is okay to have the sampling interval. And then it's perfectly okay to do this, to have a local device controller that is also an MPC controller. But also here, of course, you have the risk that also this one won't arrive at the feasible solution. And in that case, you also need a backup here. So you still need this linear quadratic control. Then we have the switching strategies. How should you switch from the cloud MPC to the local controller? There are several possibilities. You can switch instantaneously. As soon as you lose, as soon as you don't get any response back, you can run a linear quadratic controller and switch instantaneously. You can also run an open loop during some time window, switching time window. And what you do then is you use the control signals sequence generated from the last successful MPC request. because remember that the MPC doesn't return only one control signal, it returns a sequence of control signals. And then, of course, you can use a weighted combination of these techniques. As soon as you have switching in control, you always run the risk of getting what's known as switching-induced oscillations or switching-induced instability. And that can be reduced by introducing a dwell time. For instance, saying that you cannot switch instantaneously back from local to cloud. You have to stay in the local a while to ensure that this type of problem doesn't happen. Okay, how do we handle delay variations? We use buffering, and that's a classical technique. So at time k, we sample the plant, and then we estimate what the state will be at time k+1 at the next sampling instant, giving the information that we have available at time k. And then we send the MPC request that corresponds to the one that we would like to send at time k+1. We send that at time k up to the cloud. And then between time k and k+1, we wait for the response from the MPC. And then at time k+1, we output the first control signal from the MPC response that we hopefully have obtained during this interval. If we have a late response or no late response, that's discarded. And if we don't have any response at all, then we switch to the local controller. This approach can be extended to longer time delays also. Okay, then the final trick here is frequency adaptation. And that is to handle these fairly large variations in computation times and communication times that you can get from the cloud. And what we do is that we dynamically adjust the sampling rate of the MPC controller based on the percentage of lost or late responses, and we call this the loss rate. And we do this with a very simple PI controller, where we use the loss rate as a measured signal. So we calculate what the loss rate is in percentages. We use the control signal as the sampling rate of the cloud MPC, and we have a set point of 0.5% normally. So here you see the overall strategy. We have the MPC that sends its requests up to the cloud, and we have a frequency controller that controls how often this should be done. The plant that we have tried this out on is a very, very small and simple plant, a linear ball and beam process. And of course, this is not a realistic plant for MPC control, but it's a plant that we have readily available in our lab. Here we see results. So we control the position of this ball on the beam with a square wave as a set point. And we switch where we use function as a service, and we switch where in the cloud we execute these functions, and the function then implements the optimization. And we have 4 cases. Either we use a local Kubernetes cluster with 7 nodes, and there we have a median delay of 11.7 milliseconds and 12.8 as an upper quantile. Then we have our local research data center, the Ericsson Research Data Center in Lund, that is located very close by the client. And there we have about twice as long latencies. Then we have the central node, which is Amazon Web Services node in Frankfurt, giving us 37.6 in median. And then we have North, which is Amazon Web Services data center in Stockholm, which gives us 180 milliseconds. And here we randomly, well, maybe not randomly, but we changed the target. We changed which node we evaluate this function as a service optimization on. And we see there at the local Kubernetes cluster, which is the fastest one, we have a fairly large sampling period. But then if we go down here to a slower, far away node, we decrease the sampling interval of the MPC, and so on and so forth. And here we get up to North. North is the one that is the furthest away in terms of time, so to say. And here we have to go down a lot in frequency. Actually, so much so that the performance suffers. So this is not really ideal. So this was the use of very conventional cloud technology, very conventional software stacks. We use function as a service, and the system is also robust towards resource starvation caused by contention for the resources and large variations in network load. But I didn't show that. So then finally, how should we use these infinite compute resources? Well, one could use a more detailed, possibly nonlinear model. We could use some time-consuming machine learning approaches. But you can also, in our case, use, in the MPC case, we can use what's known as variable horizon control. Which prediction horizon to use is actually a non-trivial issue in model predictive control. You normally have it as a constant value. And in some applications, you want to use an as short horizon as possible, but that may not give a feasible solution. In others, a long horizon is desired, but a long horizon means a large optimization problem, and it means that it takes a long time to solve it. So maybe you don't have time to do that. The solution that we have tried out is to send out a set of parallel MPC requests to the cloud, because if we now assume that we have infinite resources, we can send out 5, 10 requests instead of one, each with a different horizon. And then we use the most suitable result, longest or shortest, that is returned in time and applied to the plant. We can also use this infinite compute resources to handle large variations in delay. I mean, in the way I described it, we assumed that we always had one sample delay. We designed the system to get one sample delay using buffering. But if we have larger, I mean, then maybe we can design the system to have 2 sample delay or 3 sample delay. But if we have large variations, it would be good to have a system that is designed for 1 sample delay when the actual delay is smaller than 1 sample, designed for 2 sample delays when the actual delay lies between 1 and 2 sample. And we can also do that by sending out parallel MPC requests, each one assuming a different latency. And then again, use the most suitable result that is back in time and matches, so to say, what we want. Okay, conclusion. The cloud provides both challenges and possibilities. Many of these have to do with latencies and reliability. There are at least 2 research directions. You can try to make the cloud more predictable, more real-time-ish, or you can try to make the controllers more resilient towards cloud-induced uncertainties. And there are ample opportunities, both for the control community and the computing and network community to work in this. Further information, as I mentioned, there is a forthcoming PhD thesis, December 20, on this, and these are some of the papers in the thesis, but there are more. But these are the ones that best correspond to what I've been talking about. So that's my 30 minutes. Thank you.
Oh, thank you very much, Karl-Erik. And we have one question already from the audience, Zainab.
Hello, yes. Can you hear me?
Yes.
Yes. I have some, not just questions. I need to have like some more information about some of the figures, if you don't mind.
Sure.
Thank you.
I'm not sure I can answer them. You have to wait.
Okay. No, but your presentation was very good in a
I
way
think
that
it was this figure you meant.
Yeah. Well,
yeah, I
yeah.
guess so. I cannot answer for all these alternatives. You have to look in the thesis.
Okay. So, but I got many information in general from your presentation, which I should say thank you so much. And my question is more about that part on top, which is theoretical and measured.
Yeah.
And then there are like different things that at the bottom, which I'm not sure that. Do you mean that this measured is something that has been implemented and measured?
Yeah.
And the theoretical is the thing that you have like assumed to be.
I think we have calculated, assuming certain things. I mean, the lowest one is light, speed of light.
Okay, and okay, and there is one more thing about towards the end. There was a slide, so its title was frequency adaptation.
Frequency adaptation, yeah.
Adaptation. Not this one, I guess. Maybe, yeah, this one. Okay. So this is just a question to make sure. So here, as you said, that you have Kubernetes, local Kubernetes cluster with 7 bare metal nodes. If I'm wrong, please correct me. As far as I understand, here bare metal means that you have devices that they have operating system, but they don't have virtualizations.
Yeah,
so,
correct.
like you have Kubernetes and the nodes in the cluster are like Raspberry Pis or a laptop without using virtual VMwares. Is that true?
Yeah, that's true. That's
okay.
true.
Okay. But is there any reference for these 2 figures, this one and the other one, that I can just go read the papers or?
Yeah, I mean, it will be detailed. If you can wait until December 20, it will be detailed in the thesis.
Okay.
There is also a journal manuscript in submission now, but I actually think that the thesis comes out before the journal submission.
Okay, but can I have these 2 references in the chat, maybe copied in the chat or somewhere?
You mean this too?
Yeah, yeah, because these figures are things that I wanted to read more about them. So if you can just copy paste them.
Yes.
I really appreciate it.
Maybe Alessandro collects the slides. I don't know.
I can collect the slides and then I can send you the slides also sign up later.
Thank you so much. Thank you.
So now it's in the chat.
Thank you.
We have another question. Now we are starting the break, but we have also another question from Ivona.
Yes, thank you. Just a short question. Thank you very much for the very interesting presentation. My question is to one of the, I think first or the second slide, where you had this list of different control mechanisms like model predictive control and then reinforcement learning. So what would you say when the model predictive control suits and when the reinforcement learning suits better? Do you have a kind of a...
No, I mean, reinforcement learning is very popular and hyped, I would say, these days.
Mm-hmm.
You can do a lot with model predictive control, which you can do maybe also with reinforcement learning, but
because my talk is
a large amount of training.
Yeah. So I just want from you, because you're really deep into model predictive control, so better you can say these are the use cases or characteristics or where this is definitely the better choice. Or do you know about the papers having comparative analysis of both?
Yeah, I put it in the chat. Ben Recht, I think he is at Berkeley.
Okay.
He has written papers, excellent papers, where he compares what you can do with MPC and what you can do with reinforcement learning.
Okay. Mm-hmm. Thank you very much.
So thank you again, Karl-Erik, for the very nice presentation, and thank you also the audience for attending. Now we are entering a 15 minutes break, so we are starting at 15 past. And I will share the program so that at least this is going to stay here for the break. And then I will talk to you at 15 past with Ivona's presentation. Looking forward to hear Ivona's presentation. Welcome back, everyone, from the break. Now we have the interesting talk by Ivona Brandic from Vienna. The stage is yours.
Okay. Thank you very much, Alessandro. So thank you very much for the invitation to give my talk here. And I will discuss about data-driven techniques for fault tolerance in edge computing systems, and I will focus more on the theoretical part. But I have mercy with you, it's Friday evening, at least in Europe, and I will give also practical examples and try to put, I would say, a broader perspective on the problems and challenges that we have in edge computing. I would like to start the presentation with a general, I would say, paradigm shift that we have now in computer science. And if you look at this slide, you can see the paradigm shift that we have, how our programs are written. In the past, we actually had a programmer taking data and rules and generating a program that gives us answers on different questions that we have. But today, with the increasing amount of data-driven, near real-time applications, we have completely different paradigms that is based on artificial intelligence and machine learning, where we basically have data and answers as input. If I'm just thinking about self-driving car, I already know the answer, right? I don't want to crash with the wall, right? So what I want to learn and what the system has to learn is how not to do that. So how to avoid crashing with the wall. And this can be learned from experience, by observations. And the general difference between the two systems is that the AI and ML-based system are time sensitive usually, they are data intensive, we have to analyze huge amounts of data to learn the rules. They are often geographically distributed. If you think about smart grid or intelligent traffic control or self-driving cars, we have multiple components that are geographically distributed. Plus, we have the problem on stationarity, and I will talk about non-stationarity later as well, because this is a serious issue. Because once you learn a model in smart grid, on self-driving cars, wherever, it doesn't stay valid forever. Because if the data distribution changes, if the environment changes, you have to relearn it again. And this means that we have energy intensive system and that we have explosion of energy demands. And in this talk, I will try to explain in general, what are the problems that we have in our ICT systems regarding the explosion of energy demands and how edge computing fits into it. And I will also try to give you an idea how we can deal with such geographically distributed large-scale applications with edge computing, where we also can take care of failures and, for example, failures in communication that we might have. Why is energy consumption such a big issue in general in computer systems? Here are just some pictures that you, numbers that you might have. In 2012, we had around 500,000 data centers worldwide that had electricity consumption of approximately 30 nuclear power plants. And the cryptocurrency activities today have equivalent energy consumption of states like Singapore or Iraq. And the CO2 footprint of video streaming is equivalent to the CO2 footprint of Spain. And there are estimations that the data centers of the world will consume 1/5 of Earth's power by 2025. And I did also some calculations that since 2020, all Austrian hydropower plants that we have on Danube are used to cover the demand of IT electricity. So these are the numbers. So what does it mean? What are the problems that we are faced now with it? So the first problem that we have in general in computer science is that the locality of IT changes. And if you look at this picture, this is Rimac car. It looks very fancy, and it is very fancy. It has AI-enabled collision risk prediction, automatic braking, 8 onboard cameras, 6 radar emitters, 12 ultrasonic sensors, IMU sensors. I have no idea what it is, but this car has it for autonomous driving. Then 4 levels of autonomy, and it needs a computer power of 22 MacBooks Pro on board to process all these produced data on demand, and it produces the sensors generate around 6 GB of data every hour. So you can now discuss, is this a car with a computer on board, or is it a data center on wheels? We can have a very nice discussion on this. And then I would like to show you a video. And this video is provided to me by one of my colleagues here from Vienna University of Technology, Hannes Kaufmann and his team. And what they are doing, they are developing virtual reality systems. And what you can see here is multi-user virtual reality system, and it's very, very powerful, because by using this system you can have 5 people that are on 5 different continents and they think they're in the same room. So the doctors, for example, can practice new surgery procedures, or you can use it for gaming, for tourism, for education, many different purposes. And why I'm showing you this video is actually the laptop that you can see here on the backpack. And the reason is that if you want to produce videos of quality, you need to produce 50 pictures per second. And if you want to process so much data like these people have on their body with the sensors, the computation has to be so close that not even edge computing can help you here, right? So this is the reality. This is the reality in that people dealing with virtual reality and augmented reality are faced with. Why I'm showing you that is also the reason that data centers that we are using today, they are changing. So most people imagine data center looks like shown on this picture. And this is a data center, but we have many different forms of data centers. What you can see here is also data center, and it's an underwater data center. It is experiment by Microsoft, where you put whole data center underwater and you can save cooling. I'm not sure whether this is already in production, but it is at least an experimental development. Then we all know micro data centers that you can put into the corner of your office, so you have your data close to you. We know Raspberry Pi gateways where we have where we can do small computation, I don't know, data staging, whatever, but still we can do some form of computation in the vicinity of the users. High latitude data centers, liquid cooling data centers. So the data centers have different forms and flavors and different geotemporal conditions that we have to put into equation when we are dealing with large-scale distributed applications like machine learning and artificial intelligence that are used to steer cars, for example. So the next issue that I also want to discuss with you, it's also related to edge computing, is the evolution of human behavior. And what do I mean with that? It's actually shown on this picture. And what you can see here is a forecast how the energy consumption will change or increase in ICT, and it's not a random journal, it's Nature, published 2018. And I mean, there are some very interesting observations that we can see here. On the one hand, if you look here, the production of ICT will cost the same energy in the future, right? So this is not significantly increasing, the red area. The yellow area here is the energy demand for the consumer devices, televisions, computers, mobile phones. And this is going to decrease in the future because our end devices are getting smarter, they are getting smaller, more efficient, even though we have much more of them, right? But there are two very interesting and very, I would say, concerning developments. On the one hand, we have explosion of energy demands for data centers because we put everything into a data center, everything is in a cloud, everything what we have on our smartphone is actually in the cloud. We have our replicas and so on, everything is in the cloud. this is one thing. So we need more energy to operate our data centers. And guess what? We have to access all those data in data centers. So we have also explosion of the demands for the networks. And this is the blue area here. And I have to say that these forecasts were done before COVID pandemic, before everyone used streaming. I mean, we are now, I don't know how many people are streaming today, this tutorial. So usually we would sit in a lecture room and listen what I'm explaining to you, but now we have, I think, more than, we have 30 streams now. So 30 people are streaming now my lecture, and we need electricity for that as well. So we have in general a problem of changed behavior that people have. And this is also another view on this development, and you can also clearly see how we have an explosion of energy demand, in particular for the networks, right? And the concerning fact is that this share of the total energy demand for the overall energy demand is going to increase for ICT, right? From very low share here in 2050 to around 1/5 that will be in 2030. And what I also want to show you here, if you go to the website of International Energy Agency, you can also break down the CO2 emissions for an hour of streaming based on the country where you are. So I did it for Austria. You can choose the tablet or smartphone or television and different network types and so on. And you can compare it with the CO2 emission of boiling a kettle, right? Just to have an idea, what does it mean now to use the networks and to use all those data centers. And you can see here in Austria, we get the major share for the electricity when we are streaming is for data transmission. And here's another picture where I have South Africa. So we have now, instead of 11 a gram, I don't know what is the share here, but instead of 11 for Austria, we have 69 for South Africa, because they have fossil fuels and the energy is produced by fossil fuels. And then you can also check what happens if we have now another end device, if you have a big screen, right? So you can immediately see what is the CO2 equivalent for the streaming. So I can just recommend you to check this website and get a feeling what does it mean. Okay. Another issue and the problem with IT, and you will see later whether cloud computing and edge computing can somehow help with this issue, is that electricity is the only power source for IT. And this is increasingly a problem because I cannot substitute my power source for my smartphone and for my laptop. I cannot put hydrogen or whatever, because I think the converter would be, I don't know, 10 times as big as my smartphone. And just to show you, if you tell me now, but we can produce green energy, and this is anyway what is happening right now. So you need so much wind generators in order to replace one nuclear power plant. So the question here is also whether we have the resources and the place to put all those windmills. And another picture that I want to show you is the global direct primary energy consumption that we have in the world. Because when we are using smartphones, laptops, whatever, many people cannot imagine that actually there is a CO2 footprint, and there is a really huge CO2 footprint. And you can see here the development of the primary energy consumption and the source of the energy that we have, like traditional biomass, coal, oil, gas, nuclear, and just this small fraction here, like from here to here is green, right? And why I'm showing you that, because in European countries, we have green sources. Like you can see here in Norway or in Austria, we have a really huge share of hydropower, power plants. But if you look into countries that are under development, like Sri Lanka, India, or Iraq, the energy is mostly produced through fossil fuels. So in Iraq, there is oil, in India, coal, and in Sri Lanka also oil. So in those countries are as well getting digitalized, right? So what is the role of edge computing here? We will see, especially if you consider that the architectures that we use today, so everything what we use today, right? Everything what we use today, smartphones, computers, laptops, cloud, edge, is von Neumann architecture that has significant problems with the separation of data storage and the processing, CPU and memory. So there are future architectures, and there will be different future architectures, also depending on the how to say data access, which might be high rate of data access or low rate of data access, and also the precision of computing. So there are different types of computation that you might have, right? Like scientific computing, solving linear and partial differential equations that has high or requires high degree of precision. But then at the other end, you might have very low degree of precision if you are generating random numbers. So why do you need a precision? It can be very low, level of precision. But the question is also which architectures can be used here for random number generation. So also in terms of different signal processing, optimization, and machine learning, there might be also different level of precision that we might have in the future. Why I'm showing this slide is that no matter which type of architecture we have, quantum computing, neuromorphic computing, approximate computing, we will have different localities where our computation is performed, right? We might have, if you look again at this virtual reality setup, you might have, I don't know, maybe some implants in our body. Maybe it is here. Maybe there is an edge data center. There is a massive data center. So the network will be the bottleneck in the future. So, and this is also why the role of edge computing is so significant here. So even though we might have very efficient and also very fancy architectures, we have to communicate, and there is physics that we cannot do better than the physics allow us. So, and that's what I'm showing you that. And then there is another problem that we have, and another problem is that we have significantly decreased trust in the IT devices in our IT world, and for that reason I show you this slide. I don't know whether someone already saw that, but this is a motherboard from, I think, produced in China and bought in US. And then the US engineers, they took everything from the motherboard that is in specification, and they figured out there is a small red dot on the motherboard. So does anyone know what is that small red dot here? Anyone? Any ideas? I have to look at the chat. Okay. Well, it's actually a chip, right, that was installed, but not in specification, that was used to infiltrate all these companies. So all the data was sent somewhere else, right? Yeah, so the question is now, how can we avoid that? Because how can we increase trust in our ICT? Because we cannot trust even a motherboard that we buy, right? So what we have now is also explosion of encryption, decryption, higher energy demand for CPU. And that is maybe also the reason why, just a moment, why the European Union has declared to invest 8 billion euros in supercomputing to produce their own motherboards that we don't have yet. Okay, so the question is, how can edge computing help us with all those problems, like decreased trust in IT devices, evolution of human behavior, locality of the IT, and the fact that electricity is the only power source for IT. Well, let's see where we can do some improvements. So this is the architecture, how I see and how I position edge computing in this whole landscape that we have in our IT. On the one hand, we have different applications that have very strict requirements, for example, latency for vehicular networking, cyber-physical systems, virtual reality with very, very low latency, personalized medicine, robots. And then we have this continuum of device infrastructure, internet infrastructure, and massive data centers. And if we don't have enough power, if we don't have enough computational capacities, we can process data here. If they are not powerful enough, we install small micro data centers. And what I address also in my research is so-called in-transit computing, where we dynamically decide where the data is processed. Some parts are processed here, some parts are processed here, and some parts are processed here on demand. That is decided dynamically. So if we now process the data here or here in the vicinity of the end user, we might increase the trust in our devices because we can process the context information already here. So we don't store raw data in massive data centers. We don't put raw data on the travel through the network to the remote massive data centers. We maybe send only aggregated information. So using these edge nodes, we can increase trust in our IT, in our ICT systems. Then we can effectively increase the problems with the locality of the IT and deliver solutions for latency sensitive applications. We cannot change the fact that electricity is the only power source for the IT, so we cannot help on this issue, but we might help a little bit on the evolution of the human behavior and the streaming, because we optimize some parts of the streaming behavior, content delivery, and so on and so on. So we make it more efficient. So, and on top of all these problems that we have here, we have now failures that might happen, and failures can make everything even worse. The edge systems are also error prone. There is just one example from Amazon Web Services that every 100 milliseconds delay costs around 1% of the sale. Plus we have here extreme low latency. We have ad hoc networks, different type of failures that we might have in other types of different distributed systems, but also that are very typical for edge systems. We have here unstructured, dynamic, and heterogeneous architectures, where the approaches that we know from other systems, for example, retry or checkpointing, or rescheduling doesn't work because we don't have time to reschedule if we have latency of 100 milliseconds, right? Plus we have lack of traditional support systems for like diesel generators, fully duplicated electrical lines. So we have to learn to live with failures of the systems. And on a such scale, if you have a geographically distributed edge systems, failures are not exception. they happen on a regular basis. So they have to integrate failures into the overall application behavior. And Atakan will speak today about very specific approach that we have here for spatio-temporal dependencies, where we combine common knowledge and also non-deterministic dependencies. That means common knowledge is something we know. We know if we have power outage, then our computer doesn't work. But there are also non-deterministic failures in our system that, for example, 2 servers always fail at the same time. We don't know why, but it is the fact, right? And he will show you approach how to infer in that systems and how to achieve certain requirements, for example, availability of minimum 99.9% of the service time. I'm going to explain you another approach here, and this approach is how can we deal with system failures? How can we deal with behavior of an application, geographically distributed application on cloud, edge, and device continuum if we distribute it or using our device, using edge and using cloud, plus all the problems that applications in real world environments have. And the failures and means, for example, if we cannot reach a certain object or if we can reach a certain person, is integrated into the whole process. Okay. So let's start here. I would like here to start with an example, just to understand and to give you an idea that, about the problem that I'm addressing here. And we assume here the problem of electric vehicle data analytics. So what is the problem here? What do you don't want to have if you are driving electrical car? What do you don't want to have? If you have an idea, just write it into the chat, I will check. Well, let us assume you have here electricity producers and you have cars on the road. You have electrical cars on the road that have to be recharged from time to time. Yeah, stop in the middle of the street, exactly. That's what we don't want to have. This is one thing. Another thing is you don't want, I'm sure if you would have maybe you have electrical vehicle, but if you have electrical vehicle, you don't want to wait too long on the charging station. You want to be charged when it suits to you, when you are, for example, doing grocery shopping or when you are in your office. So you really want to have these recharging intervals to fit your need. And this is actually what we want to achieve here with electric vehicle data analytics. On the one hand, we have electricity producers, and in best case, we have electricity from the green resources like solar power or wind power. And you know that electricity cannot be stored for a long period of time, and the natural resources are very volatile. Sometimes we have sun, sometimes we don't have sun, wind, and so on. So you have a kind of a big data analytics here, trying to deal with the smart grid, with the prediction, with the production of energy, and also with the demand of energy. And now the electrical vehicles comes into the play. So you have your electrical vehicle and you want to make inference of this on this big data model that you have here, but you have so many vehicles on the road and you have distances, you have not enough bandwidth, the infrastructure is maybe not optimal. So you have the roadside units and maybe some edge servers. So you put the local version of this model on your edge server. And now when the car is in the vicinity of an edge server, the car can do the inference and check, okay, where is the next charging station that I can use? And on the other hand, the edge server can collect the data from the car, like velocity, battery status, driving directions, and so on and so on, changed directions, whatever. And also update the model that you have here on your edge server. So what is the problem here? When the car is here, the car can see only this local version of the model, but it cannot see what is happening here and the updates here and also the updates here. So there is a kind of insularity, insularity problem. Another problem is that, as I said, the environment changes all the time. The conditions on the road changes all the time. There might be accidents, someone changes direction and so on. So the models that you learn, they are not valid for a long period of time. So you have non-stationarity because the data distribution changes. So you have to update your learned model and have the freshest model at the roadside unit so that you make inference on the most freshest version of the data that you have. And then there is a third problem is that cars are not always reachable, and they have intermittent connectivity, and you have to deal with that. So there are sometimes in rural areas where you have nothing, you have no cloud, no edge, no 5G, nothing, and you have to cope with that. So with the failures, with not reachable subject on the road. And the problem is now, how can we steer the cars on the one hand, and on the other hand, how can we deal with these difficulties with local prediction models? By the way, this problem and also solution is presented in our Sigmetrics paper 2020, and you can find also a presentation by Atakan Aral, also on YouTube, I think. It's a little bit shorter than mine and more focused, but you can also find it on YouTube. So what we are addressing here is edge data analytics. And here is, I would say, a very generic representation of the edge data analytics, where you have a parameter server, where you have streams, and this can be vehicles, and the vehicle, they send the data to the edge nodes where you have the local version of the model. Now you have the streaming data, you get new data, you can create a fresh version of the model, then you update the local model, and then you redistribute again the freshest version of the data to all edge nodes. And this is what we call edge data analytics, right? So what we want now to achieve here, I mean, this wouldn't be a problem if we would have computational rich environment like edge, like cloud data center, but we don't. We have insularity, we have non-stationary, we have intermittent connectivity, and it's geographically distributed. So the question is, how can we achieve high quality of our analytics with minimum communication overhead and with similar accuracy as core data analytics? And this problem of edge data analytics is very generic. So steering electrical cars on the road is just one example. Another one is also 36-degree video head movement, where you have to speculate on the movement of the head. So you cannot download all 36 degrees all the time because you don't have enough bandwidth. So you have to learn the behavior, and you have to speculate on the behavior of the person in order to save bandwidth, in order to download the right fragments of the videos. I will explain you this stateless control, we call it stateless control problem, with a very simple example so that you really understand what is the problem here. You can now assume that we have 4 vehicles on the road, and we have distributed certain version of the model on our roadside unit, and this version of the model has certain accuracy. It's very accurate, but it drops down over time because it becomes stale. The data are old, right? Now you can assume that we receive updates from the vehicle 0 and 1 at certain time point t0 here. Now we can update the model, redistribute to all roadside units, and then we have higher accuracy. But then we can decide, no, we will wait until time point 1 when we receive the update of the vehicle 3 that is also on the road. Then we have even higher accuracy of the model here, but it drops down over time again. Or we can say we wait until we receive the update from the last vehicle on the road, which is vehicle 2. Then we have even the highest accuracy of the model, but we suffer here from very, very low accuracy. So you can now guess what I'm trying to do. I'm trying to optimize the area under the curve. And this is very tricky because everything what is until T0 we know, we can calculate, but everything what happens after T0 is not known. We don't know when which car will send updates. We don't know the order of the updates, and we don't know also the value of the updates. Maybe there are updates, but they don't have any value for us. And this cannot be obtained a priori. So it has to be modeled stochastically. And this can be applied to many different areas. And we have trained, we have found similar problems. For example, when you use the sources of training to predict the accuracy of flights in an airport. So if you include sources into training, right? If you have only one source, then the prediction is good for this source. If you include, let's say, if you have 10 sources and you gradually start increasing all 10 sources, then you have even higher accuracy, right? But the question is, do we have to have all 10 sources for the prediction of the flights? Or do we have only to have 5? Maybe 5 are enough. And we have still good prediction of the flight delays. And this is the problem that we also want to solve here. Basically, this picture shows what I have shown here. It's the same, just represented as Markov decision process, where we have updates from both cars. Now we can decide to wait to receive updates from the third or from the fourth car, or we can say, no, we push, we redistribute the model. If we receive the update from the third car, we can say, okay, we redistribute our updates. So everyone has now the fresh version of the model, or we can say, no, we wait until we receive all updates. And when we receive all updates, we can still wait, but this makes no sense. So we wait in vain, or we can push the model and redistribute it to our vehicles. And this is a Markov decision process that we model here, which is discrete time stochastic control process that has partly control, but also partly random outcome. And we model it here as a quadruple. We have states, which are given as binary string. If the update is delayed is 0, otherwise is 1. We have a set of actions, which are wait and push. We have transitions between the state, if certain action is executed, and we have a set of rewards. So we reward behavior or we give penalties if the behavior is not good. So what we are trying now we are trying to learn which path is the most feasible for us here, because we might have here infinitive set of paths that we might follow here. So here is now, if we have only 2 cars, if we have 3 cars, and if we have 4 cars. So the problem that I'm describing here, we implemented with Q-learning. And to refer to the previous talk, one could use control theory here, which is not really feasible here because of the number of different inference rules that you have here. So the machine learning seems to be more feasible solution, and Q-learning allows us to learn a policy, which is a sequence of actions rather than independent actions at each state, where we can model individual connectivity, relative connectivity, update significance, which is actually what we need in edge data analytics. And here we involve an agent performing actions at each time step t. An agent is provided with a reward, and we aim to maximize the expected values of the total rewards over time. And you can see here, we equip here learning rate, our agents with a learning rate, and we have also discount factor for the future rewards. And you can also see that here the rewards are measured as a utility if we execute push, so if we update the model. It is 0 if we decide to wait. And if we wait, but we are in this loop and there are no further updates, then it's a penalty, right? We give certain penalty. The question is, how can we evaluate the solution that we are proposing here? There are 2 ways. Both ways have advantages and disadvantages. We can say theoretically much about the solution because we use Q-learning, and we can say much about space and computation complexity. We can even say much about sample complexity, and sample complexity means how probable is that we are able to learn the right policy. And in Q-learning, we can say that we are able to learn the right policy that is bound to a certain error rate, right? So this is something we can say. But then there are a number of questions that we cannot answer theoretically. So does SCADA, which is staleness control for edge data analytics, this is our abbreviation, does it make timely updates? Does it make significant updates? Does it make mistakes? Do we have high accuracy of our results? How does it compare to state of the art? For example, if we have fully synchronous approach where we update after each, where we redistribute the model after each update is achieved, or whether we have completely disconnected approach where we don't do any updates. So how do we position ourselves compared to the state of the art? And then the question is, how sensitive are the results to the chosen parameters? And this is something that we can do only using empirical evaluation. So we have also very thorough empirical evaluation where we focus on the cumulative age of information. If you consider a time frame of 180 minutes, then the cumulative value of information updates, then we consider here silhouette score in terms of accuracy of our analytics. So we measure also the accuracy of the analytics, and we don't have ground truth here. So we use clustering approaches here, and we compare here to fully synchronous and to fully disconnected approach, right? So I'm skipping the theory. You can check it in the paper. What I want to show you here is, for example, how we checked the penalized weights and the distribution of broadcasts. So you can see here different approaches that we use here. So here we have the staleness control approach. Here we have quorum, where we have to achieve certain number of updates. Here is a certain threshold that we want to achieve in our accuracy. And here we assume the similar connection like in the previous iteration. And you can see here that we have very, very few updates considering and compared to other approaches, having a comparable accuracy of the computation and of the prediction. The work that I have presented here is one of the major results of our FWF START project, runtime control in multi-clouds, and we have many different papers that are related to this staleness control, so you feel free to check them. And as I think that my time is already done, I'm just jumping to my last slide, and I might explain you the edge in action at some other conference. So summary, future work and challenges. Well, I have shown you how edge computing can be used as a solution for computation with latency, privacy, and bandwidth issues. Some difficulties when it comes to failures due to timeliness, but I have also shown an approach how we can integrate the failure handling into the overall communication approach using machine learning approaches. If you need now some questions for further discussions and for thinking, what I'm asking myself is how all those challenges and problems will change if we assume completely new architectures also in communication, so with low orbit satellites. So we have now several thousands of them, if the computation that we know using these internet architectures changes to satellite-based computation, where we have different endpoints that communicate over satellite. So discussion maybe for the future talks. What is going to change? What does it mean for edge computing? Thank you very much.
So thank you very much, Ivona. I am making a virtual applause, so that's the best we can do nowadays. But it's a very interesting line of research that you are working on, and I'm also looking forward to the hands-on part by Atakan.
Yeah, Atakan will focus on a little bit different. He will focus on making inference to the system when you learn on the system. I'm not talking about this now, so you have to attend this talk.
Exactly, but it's a good pitch at least, so that people will understand, and then you create some expectation now. That's very good. So is there any question for Ivona? In the meantime, I see that Atakan also posted in the chat the link to the YouTube presentation of the Sigmetrics paper that Ivona was mentioning in her presentation. So feel free to go and check it out as well. I have a comment also related to your presentation. I mean, at some point you were mentioning about the reinforcement learning and the possibility of using control for doing something similar, and that relates also to your question that you had before for Karl-Erik.
Yeah.
So in general, it's a comment. It's not really a question, but I would say that at least for the problem that you have there, it seems that at least the approach that you have seems a bit more suitable than maybe using an NPC or something similar. Mostly because whenever you have some discrete variables, and when I mean discrete set of decisions, then these are typically more suitable for reinforcement learning approaches, while whenever you have some decisions that can be quantified with a continuous variable, then reinforcement learning suffer from the curse of dimensionality, meaning that you will need to discretize these states or these decisions, and then this will increase the complexity of training and this type of stuff. And that's why, for example, control approaches could be a better approach for this type of problem. So that's somehow a line that I would draw, for example, to distinguish the two.
I agree with you. Yeah, I was just thinking also in these terms. I mean, it would be also nice to have a kind of I don't know, survey or paper focusing on that. But yeah, this is something we can do later. Yeah.
I can send you a paper that looks into this direction, not too deep, but at least compares different approaches. Good. Do we have other questions from the audience? You can raise your hand, or you can type the question in the chat. I know that this format is a bit strange. If you were like physically present in a room, that would be much easier. But don't be shy and ask questions to Ivona. I have actually another question that was somehow bugging me during your presentation. So you started presenting a number of figures related to energy consumption, and then at some point, then you started speaking about your reinforcement learning approach. And in general, I am thinking that I have been reading a lot of interviews from, for example, Amazon, saying that deploying machine learning applications, for example, in the cloud, is kind of quite expensive in terms of energy consumption. So do you think that it is somehow like a recursive problem, that in order to consume less energy, then you are trying to optimize something with machine learning, but then you are shifting the problem to the complexity of, or the energy consumed by the machine learning algorithm that is solving the initial problem? Do you understand my question?
Yeah, you're trying to optimize the system with a method that is basically very bad, right? And consuming energy on its own. You know, the thing is that you are trying, I mean, if you think now about these energy and electrical vehicle problem, we are trying something that you cannot solve with other things. We are solving it with reinforcement learning that you cannot solve with other things. So, okay, then if we solve it, maybe the people are likely to use electrical cars. And then we have savings on these fossil fuels. You know, the problem is so complex, you cannot see it in one dimension just by addressing the computational resources. You have to see it on the whole, you know, holistic. I hate this word holistic, but you have to see it on a holistic scale. Maybe machine learning is quite expensive and reinforcement learning and what we're using here. But on the other hand, it might be the boost for utilization of electrical vehicles. So.
Well, that is definitely a very good answer. I mean, I don't have. Yeah, go ahead.
Yeah, another example is also what we are doing is arbitrary computing, right? So arbitrary computing where you utilize, instead of dedicated edge nodes, stationary edge nodes, you utilize piece of laptop or smartphone that is somewhere around. In order to do that, you have to use smart contracts or blockchain or something like that. Again, you have this layer overhead, but you know, even if you have this thick layer, right, organizing and giving this kind of business logic here, you might save from the production of another server. So you produce less server, you save resources for everything what is necessary. So the the calculation of the impact, it's really difficult here.
Yeah, it makes a lot of sense. Maybe since we have the time, in the meantime, that other people may have some questions, I can ask also another thing, because I'm really interested in what you're doing. Do you think that the current computation models are somehow providing a good infrastructure for going towards a more sustainable computing? And I mean that with this, that right now there is somehow no API, for example, for the developers to specify that their computation, for example, could be less important than other types of computation. And then in principle, I'm okay in having the results of my computation in a bit longer time, but using more sustainable energy, rather than, for example, no, this is quite important, so I'm okay in going for any type of energy that you can retrieve, but I need the computation now. So there is a differentiation in terms of the application. And right now I don't see any way of specifying this, and this information could be extremely helpful for example, the development towards a more sustainable computing.
Definitely. I'm not aware of any project in this area that is focusing exactly on that. If you think from the scientific perspective, that
yeah, I'm thinking about scientific, but also on the technological perspective. But I think that could be something very interesting to discuss.
Yeah.
And I mean, we have a project now. That's very good. So yeah, if you have any question for Ivona, please use the chat, or you can also send her an email directly, and then she can reply to you offline. So I would like to thank Ivona again for your very nice presentation.
Thank you.
And I think we can move to the break 5 minutes earlier, and then we will start again 15 to 12 in Eastern, in New York time practically, or 5:45 in Central European time. I don't know about other other time zones that may have connected right now. I will share my screen with them with you should see this. This is the program, and I will talk to you soon after the break with the Atakan tutorial. Thank you. So welcome back, everyone. This is the last part of the tutorial, and I think that's also one of the most interesting parts. That is a bit more hands-on, and I would like to thank Atakan Aral from University of Vienna that will give this hands-on tutorial. Atakan, the stage is yours.
Thank you very much. So my screen should be visible now.
Yes, it is.
Okay, great. So hello, everyone, and thank you, Alessandro, for the introduction. So as he said, I will present a more practical part titled Data-Driven Techniques for Fault Tolerance in Edge Computing Systems. So there will be some mathematics and statistics involved, and we will use a machine learning tool for learning stuff from data related to failures. So I will try to make it as interactive as possible, but it is not that easy in a virtual setup. So feel free to interrupt me anytime in case you have questions. So let's begin with some interesting statistics. You see on the left side the cost of a data center failure over the years. This report by Poneman Institute, they released it latest in 2016. A new one should come soon, but we can clearly see a trend that a failure in a data center, first it costs a lot, and this cost is also increasing. Because the market is getting bigger and bigger all the time. So it started from 500,000 and in 2016 it was 740. This is the average cost of a failure, and you can also see the minimum and maximum on this graph. And maximum is always almost $2.5 million. And according to the same report, a cloud data center failure on average takes 18.5 hours until it is resolved, and its cost is around $700,000 per hour. And when we check the reasons or the causes for these failures, we can see that there is a part of human failure and natural disasters, which are harder to take precautions for. They can be maybe harder to predict, let's say. They are more unpredictable type of reasons, but almost half of the failures are caused by operational reasons, which we can do something about. We can predict this kind of failures or prevent this kind of failures, as I will show in this tutorial. So let's look at two real examples from recent cloud failures. In 2017, two S3 subsystems of Amazon Web Services were actually accidentally shut down in only one of the data centers of Amazon. They have many. In this case, it was US East 1, and it was only a storage system, S3, simple storage service. But the failure cascaded to all other, not all, but many other data centers, and also compute cloud as well. So the computation was also affected, not only storage. And for 11 hours, 54 or more than half of the top 10 online retailer services were inaccessible, which, as you can guess, caused a lot of economical loss. The loss is estimated as $150 million. And this is another statistic for also for Amazon retail websites. Even if there is no failure, only a slight delay in the services because some of the data centers are inoperational, they face a loss of sales. To be precise, for each 100 milliseconds of delay, they have 1% less sales. And of course, this accumulates as more delay occurs. So as you can see, service outages in business environment cause significant revenue loss for both infrastructure and service providers. So not only Amazon Web Services has loss, but also many services that use it. So in this very example, several services such as Adobe services, Bitbucket, Quora, Coursera, GitHub were all inaccessible for a long time. And even people in their households were not able to use their connected light bulbs or connected thermostats, which is of course quite an inconvenience too. Another very recent example, I think it was yesterday or the day before, as you most likely realized, there was a failure in Facebook services, and also WhatsApp and Instagram was affected. And of course, it is now very early to know the exact loss of revenue, but an estimation by Fortune magazine calculates around $100 million. And this is only ad revenue loss, not considering all other revenues that they have, and loss of data as well. So as you can see, cloud failures are very, very expensive, but you might think that this tutorial is about edge computing. What about edge computing? We don't have this kind of statistics about edge computing because it is not that widespread at the moment. But we argue that failures in edge computing are more likely, and we will have, if we don't take the precautions, we will have more and more failures when we use more and more edge resources instead of cloud resources. And there are several reasons why we think this. The first reason is that cloud resources are by definition centralized, which results in easier management and maintenance, while edge resources are, of course, distributed, and this results in complicated management and maintenance. Also, cloud resources are very large scale, and this gives you a high opportunity for redundant services, and you can scale your services in case the demand increases unexpectedly. It might be harder to do in edge resources because of lack of available computational capacity. Then cloud resources or cloud data centers have these advanced support systems such as duplicated electrical lines or diesel backup generators or fire suppression systems or liquid cooling, all kind of high-end technology for supporting these kind of infrastructures, which also lacks in edge resources because edge resources are by definition at the edge of the network, closer to the user. You want, and they are small in size as well, so you don't have a possibility of these advanced support systems. Network is another reason why edge might fail more frequently, because a data center network is quite robust, while in edge computing you have ad hoc and heterogeneous network. There's a difference between churn. Cloud is typically low churn and edge can be high churn. And in cloud, there can be more structure, there can be predefined risk groups, availability zones, and in edge computing, you are more unstructured and you have to be dynamic due to the changes. And Another typical reason is that edge computing is for running tasks that are latency sensitive. So for this kind of tasks, you cannot simply choose re-execution as a failure recovery method, because if you re-execute everything from scratch, you lose too much time, and the user is expecting low latency. So this you can do in cloud. Typical cloud methods for failure avoidance or failure recovery are re-execution or checkpointing. This you could not do in edge computing. Finally, the failure resilience methods that you use in cloud can have high overhead because there is enough resources. But in edge, you have to be more responsive, and you don't have sufficient resources for more complex methodologies for failure resilience. And of course, we are not saying that edge computing, in edge computing, we have to reinvent all reliability methods or all techniques for failure resilience. No, of course not. Edge providers may understandably adapt methods from cloud computing, but there is still a need for resilience technique that take these unique features and limitations of edge computing into consideration, so that we can have comparable levels of availability to cloud computing. So after this motivational starts, I would like to summarize a little bit about our agenda, the challenges I already started mentioning, but I will be more specific in the next slides. Then several how-to sections, as you can see, will follow. The first one is, how can we model these service failures? The next one is, how can we model the dependencies between failures so that it's easier to predict them? Then how can we learn these dependencies from data in an automatic way or in a continuous way? Then we will take a break after this point 4. And after the break, I will do some hands-on, not programming, because it doesn't make sense to write programs remotely, but we will use an existing machine learning tool for extracting dependencies from data. And then using this information, after we know these failure dependencies, we will see how can we deploy fault tolerance services. And by the way, I use the words failure and fault interchangeably. There are slight differences between them in theory, but for this tutorial, I will use them interchangeably. And if we still have time after this deployment section, I will also talk about how can we verify all these steps are working, they are beneficial for edge computing services. So I will talk about a little bit verification, because in failure tolerance in the area of failure tolerance, it's not that easy to evaluate your solutions because real failures are not very frequent. So you have to simulate somehow to see if your methodology or your techniques are actually working. And finally, if we again have time, I will talk about how can we combine this fault tolerance with other quality of service objectives, especially the ones specific to edge computing, like latency or bandwidth or energy consumption, because fault tolerance alone is not enough. It has an edge service also have to consider many other quality of service objectives, and I will talk about how this multi-objective problem can be solved, or one way of solving it, of course. So let's continue with the challenges. I already told you the challenges of edge computing in comparison to cloud. And the state-of-the-art solution for edge reliability is replication, or in other words, redundancy. So you replicate your services. If one replica fails, you can still serve the users from the other replica. So you are running it in a redundant way. And this also actually makes sense for edge computing, because in edge computing, you are usually targeting users in a large geographical area, so that your replicas would be in different geographical areas closer to the users in that area. So if a failure happens, the users would not have the closest edge node to them, but they can still get acceptable service, or at least a minimum level of service from another edge node that is, let's say, in the next neighborhood. So what I mean is we already have redundancy in edge computing, and the idea is using this redundancy can make sense also for avoiding failures. And when we use replication, the undesirable case is that when replicas of a service are deployed at servers that fail in overlapping periods, which means if I have 3 copies of my service and I deploy it in 3 edge servers, somehow these 3 servers fail at the same time. And we showed that this is actually possible, because in edge computing, failures can be due to various reasons that I will talk about. These failures can be correlated. They might, for example, have this same cause, resulting in concurrent failures. So this observation actually destroys my replication solution, right? Because it doesn't matter if I have 1 replica or 3 replicas if all of them fail at the same time. And the challenge is how can we choose optimal replica locations, or it doesn't have to be optimal, or better, let's say better replica locations, so that this undesirable case can be avoided. So this is the main challenge I will talk about. And there are different solutions actually for failures, node and link failures at edge computing. Ivona has already, in this previous talk, Ivona has already talked about this staleness control paper, which is actually a reactive solution. So a network failure happens, some data doesn't arrive to the data center, and we are trying to prevent negative effects or minimize the negative effects. But in this tutorial, I will talk more about a proactive solution that we call dependency mining. And particularly, I will talk mostly about our most recent paper published in IEEE Transactions on Parallel and Distributed Systems, where we propose a method to learn these dependencies from historical data or retrospective data, so that for future edge computing services, we can choose better locations in terms of fault tolerance or failure resilience. And as I said,
I have
yes,
I have a question related to this last aspect. Is the learning process happening only with the offline data, or is it possible to use it also online and then adjusting it as the data come?
In this paper, we only propose offline learning because, as you will see, this learning part is quite complex, and we couldn't yet find a way to do it efficient enough so that it can be done in an edge server. It can be done in a cloud data center, yes, in an online fashion, but we are still it's a future work, let's say, to do it in an online way. For now, we periodically retrain our model that shows us the dependencies and start using this model after some time.
Okay, thanks.
You're welcome. Yeah, so I will, as I said, talk about this paper, but if I have enough time at the end, I will also talk about this one called RS, which is more about combining, as I said before in the agenda, another problem is combining reliability or resilience with other quality of service parameters, and I will talk about how this could be done as well. So this is a very high level overview of the methodologies I will introduce today. So it starts with a failure monitor, let's say in an edge computing node, or if you have a central controller in cloud, it could also be there, which logs the failures. And these failure traces are then sent to our module called dependency learning. So this one is the one that I will talk about most today, is the data-driven part where we extract failure dependencies from data. Then this is the offline part. Then the online part, the service provider has certain requirements, such as what kind of availability is needed, what is the budget, and so on. So these requirements are sent to another module called resilience algorithms. And these resilience algorithms communicate with another module called failure probability inference, where a candidate deployment is sent. And this module evaluates based on the dependencies learned before, what would be the failure probability of these candidate deployments. And then resilience algorithms can create a new candidate, get a new probability, and so on. This could take several steps. And after a while, the resilient algorithms decide that this candidate's deployment is good enough and sends it back to the user so that the user can deploy their services accordingly. So yeah, as I said, these are the three main modules, and I will talk about each one of them actually. But as I said, the learning part is the most focus in this tutorial because it's the most difficult part actually. So part two, after the introduction, is about how can we model service failures, because to predict something, you have to first model it. And let's start with some preliminaries. Sorry. We define first a deployment pair represented with delta. This pair consists of C and S. C is a copy of the service that we are going to deploy, and S is the server that it is deployed on. So using this kind of, so we are not calculating the failure probability of a server, but a deployment pair. This allows us to incorporate failures that occur in wherever in the whole system. It could be client software, virtual platform, host operating system, hardware, or whatever else. So this is beneficial for this kind of universality, let's say. And then this deployment pair is also associated with a binary random event called F delta, which shows its failure. So if it's a binary value, so it takes true or false. If it takes true, then this deployment pair has failed. If it takes false, then it's active at the moment. Then we can model an edge service as a collection of various deployments. So various copies of this service are deployed in various servers. So capital delta is a collection of M deltas, M deployments. And each one of them is a copy of this service or a replica of this service. Again, I will use the words copy and replica interchangeably. They are the same thing for now. Then, similar to failure of a deployment pair, we can also show failure of an edge service as F capital or uppercase delta. And we are interested with this parameter actually. Sorry, not with this parameter, but the probability of this parameter. So what is the probability that this deployment or this edge computing service would fail in the future? Or what is the future availability, future estimated availability of this service? And this information can be very useful. We can use it while designing our software model, or we can use it when deploying our service. So in this tutorial, I will talk about deployment only, but I'm now talking about other possible uses of this information. Or this information can also be used in runtime. So when this probability is over a threshold, for example, you can migrate your services as well to avoid the predicted failure. And so how can we calculate or how can we model this probability? And I will show you two ways of doing it. On the left side, you see a way of modeling it as an active standby replication, which means a service is assumed to be available unless all of its M deployments fail at the same time. Because a standby deployment takes over when the active one fails. So if I have 5 copies, if at least one of them is available, then I assume that the service is available. So the probability of service failure is the union of failure probabilities of all deployments, basically. Of course, this is a very simplification. This is quite a simplification, but we could also have a more realistic type of replication called load sharing. In load sharing, all deployments are active all the time, and they share the workload, and the service is available as long as N deployments out of M are active. Or in other words, if you define a parameter K, which is M minus N, so you can tolerate K failures. K of the nodes or servers can fail, and your system can still tolerate this, and we assume it is still available. And in this case, you have to compute the subsets of your deployment of size K plus 1, and because you need at least K plus 1 servers to be active, and you take the union of their failure variables, you take the intersection of their failure variables, and then you take the union of all subsets, and then you calculate this probability. Are there any questions until this part? I know.
Yes, actually there is one.
Yeah, please.
So typically in dependable systems, we're calculating with failure rates.
Mm-hmm.
Can you comment why probabilities are also appropriate in this case?
How do you define a failure rate, and how do you differentiate it from probability? Because for what we call probability is actually historical failure rates.
Yes, okay, but it's still a probability, right?
Yeah, it's a probability that, so we assume that it's historical failure rate of a deployment would persist in the future, at least in the near future.
Okay, I mean, failure rate has the dimension of failure in time, yeah. So how many failures you have within a certain time interval. And that brings the timing dimension into the game, which you don't have with the probability.
Yes, but we define this probability for a certain period of time. It's as you said, failure rate can change over time, but then we recalculate this probability also in certain intervals, so that we try to incorporate time as well.
Okay, thank you.
Thank you very much for the question. Yes, so these two ways of defining the probability, and if you notice that in these definitions there is another simplification. We assume that this service has a single component and we replicate this single component, but in reality the services have many components, and they might have different requirements in terms of failure resilience. So in this case, we can easily generalize to a multi-component case as shown in this equation. Here, K or kappa is, not kappa, but K is the set of service deployments, and kappa is one service component. And delta kappa, which is defined here, is the set of all deployments that run this component kappa. In this case, we can simply compute the failure probability of or failure variable of this component and take the union of probability for all available components. And yet another additional part is link failures. Until now, I only talked about node failures, but link failures should also be taken into account. And for link failures, our analysis showed that the dependencies are not that significant. So for link failures, we assume that each failure is independent from each other. So you simply can take the union of failure of links on the path between each module that you deployed. And finally, we can define the failure probability of the service, this time including link failures as well, as the F delta that we previously defined, and F lambda that we defined here as the link failures. And so the union of all link failures plus node failures is the probability, failure probability of the whole service. Then the question comes, how can we calculate this probability? Because it's not that trivial, this kind of computation, because of the challenges that I introduced previously. I think someone raised a hand, so you can simply interrupt.
Sorry, this is Zainab. I might have missed this part, but are you just considering a node and link failure? Am I right? Or because you talked about services, and later I heard that you're talking about node and link failure. Did I miss some parts that you were talking about both node and service failure, or?
So service failure, we define a service as a deployment. So
okay,
it consists of a server and a service together, a copy of the server. So any of them, whatever fails, is counted as the failure of deployment. But for short, I don't repeat every time. I don't say deployment every time, but I say node, just for a shortness.
Okay, so a deployment failure occurs when a node fails, or a deployment itself can also fail. So this is actually my question.
Yes, yes.
So to me, it seems that a service can be deployed on a node, and then I assume that they might have different probability of failure. So maybe a node doesn't fail, but the service deployment fails because of something else. So that is actually my question. If I could, I mean, probably ask it. I mean, I don't know if I could make the point.
Yes, yes, but from historical data that is available to us, we cannot differentiate the reason of the failure. We only know if a failure happens, and we assume that when a node is failed, it's the failure of the node. But it does, as I explained here, it doesn't have to translate into the failure of the whole service, because service can be replicated, and one deployment doesn't mean that the whole service fails.
I understand. Okay, thank you. Thank you for the explanation.
Yeah, as I said, the next step is, this is the definition that I gave before for the active standby replication, the simpler one. I will go on with this for now, not because then otherwise the maths gets crazy, and I know it's Friday evening. I don't want to cause everyone to sleep, but yeah, that's why let's go for the simple one. And so to calculate this probability of multiple variables in intersection has two ways of doing it, or two simple ways of doing it. One of them is to assume that, so one thing I want to say first is that this F delta, is our lowercase delta, is easier to calculate. As I said, you can check the previous failure rate, previous availability. There are efficient and accurate algorithms in the literature for computing the failure probability of a single node. But when we move to a service, then it's not that easy. To make it easy, you can just assume that, by the way, these two equations are two alternatives. Let's focus on the first alternative now. You can just assume that all failures are independent. All nodes, all components, or all deployments, as we call it, are independently failing and being available all the time. In this case, you can simply multiply their failure probability and you get the failure probability of the service, which is, of course, not very realistic, also because our data shows that it is not the reality, because there are dependencies, and I will talk about the reason of these dependencies in the next slide, actually. But another extreme way of solving this problem, you can just assume that all components are dependent to all others. So completely connected dependency graph. Everything is dependent on each other. This is very computationally complex, because you have to compute the probability of each node given the probability of all other nodes. And then you have to calculate 2 to the power of cardinality of delta. So delta is the number of deployments, and 2 to the power of number of deployments probabilities have to be calculated. One reason why this doesn't work is computational complexity. The other reason is when you assume that everything is dependent on each other, you are also including noise to your calculations, because these correlations can be coincidental and only noise from your data, and you are incorporating it to your calculation. So what is the solution? you don't assume everything is independent. You also don't assume everything is dependent. You should know actually which component is dependent on, which deployment is dependent on which deployment. So you have to find out about this. So to give an example of how many calculations we need for the first one, we simply multiply all of them. So let's say this is our architecture where devices are here, then we have the edge nodes and we have the cloud nodes. And let's say for a specific service, we have 3 replicas in servers A, B, and C, or deployments A, B, and C. So here we simply calculate by probability of A multiplied by probability of B multiplied by probability of C. Only three values need to be calculated. However, here you have to calculate probability of A multiplied by probability of B given that probability of or given A, and then probability of C given B and A. So this is basic chain rule in probabilistic theory. So and these given parts have to be instantiated with all possible values. In our case, all parameters are binary, but even in binary case, you have to calculate 2 to the power of n different values, which is why I say it is computationally infeasible. So after we model the failure of a service, how can we model a dependency in a way that is efficient but also easy to interpret by humans? Because we want to also understand this kind of dependencies, because maybe then we can take precautions to eliminate some of the dependencies. So it should be also human readable. So modeling failure dependencies. But before, let's talk about why these failure dependencies occurred, as I have been promising from the beginning of my presentation. What is the reason behind these dependencies? So our analysis, by the way, our algorithms doesn't differentiate between different types of dependency. It is just, as I said, the only data we have is that a dependency is a failure happened or not. We don't know the reason of the failure. That's why we cannot know the type of dependency. But we also made another analysis to understand this problem, better. And we identified 2 types of spatiotemporal failure dependencies. One of them is multiplication, when failures in 2 or more deployments have this common cause. For example, they are sharing the same network. So when the network fails, they fail simultaneously. Or they share the power, there is weather inference, they are in the same area, and there's some natural phenomena is going on and they are affected. There are flash crowds in a certain area, so they are overloaded, or they are sharing the same controller which fails and they are inaccessible at the same time. This is the first type of dependency, but the one that is harder to predict is propagation, because it is harder because one failure is the cause of another failure. So they don't have a common cause, but one of them is the cause and the other one is the result. So the failure is cascading from one node to the other. That's why the failure might not be happening simultaneously in the 2 nodes. So one fails, after a certain time, the other fails. And in this time, the first one might be already recovered, which makes it very difficult to predict this kind of failures. So why this kind of failures, this kind of cascading failures happen? For example, one reason is workload distribution. You have a certain workload, and when one of your copies or replicas failed, you'd redirect your workload to the other one, and then this one is overloaded and it fails again. Then you go to the next one and so on. Or it could be reattempts by the user. This is something similar, but when the users don't have access to the nearest edge node, they are automatically routed to the other one and they reattempt the same task there. And as a result, this one is overloaded. Or it could be something contagious, like computer virus, for example, propagating from one node to the another. So these are the main reasons of dependency. And let's go on with a very small scale example where we have 3 edge nodes only, S1, S2, and S3. And let's assume that S1 and S2 share the same power grids, and S1 and S3 share the same network infrastructure. As a result, when we model their dependencies, we can have a graph showing that F3 and F1 are dependent to each other. The direction of the dependency doesn't matter in this case. We could have the reverse arrow, it doesn't matter. And also F1 and F2 are dependent. So the failure of server 1 and failure of server 2 is also dependent to each other. So this is a Bayesian network that shows the dependencies between different variables. But here we are talking about dynamic Bayesian networks, which also have the temporal information. So this is actually about the T here. So these dependencies are in the same time step. But there can be also dependencies in different time steps. And here, in the reasons that I showed you here, one of them was workload distribution. Let's assume that these nodes are configured in a way that when S2 fails, workload is redistributed to S1 and S3. And when S1 fails, the workload is redistributed to S3 and shown by these blue arrows. So in addition to these 2 dependencies, we now have, actually 3 more dependencies, which are in different time steps. So we have the failure of node 1 at time t minus 1, which affects a failure at node 3 at time t. So 1 time step later. Similarly, this F2 affects F3 and F1 in the next timestamp, which are shown by this workload redistribution arrows. So we have a graph that shows not only the dependencies, but also the timing of these dependencies. Then, to support this graph or to complement this graph, we also have conditional probability tables for each node of the graph. So each node here, for each node, and in this example, we provide you the conditional probability table for F1t, which is here, and it has 2 parents, F3t and F2t minus 1. So for every combination of the values these 2 parents can take, we compute the probability that F1t fails and it is available. Actually, since we are working with binary variables, it's enough if you compute one of the rows. The other one is just 1 minus the first one. But yeah, if in more general case, you have several rows if your variable can take more than 2 values. So as I said, this is only one of the conditional probability tables. For this very small example, we would have 5 conditional probability tables. But the number of rows would differ between the tables because the number of parents are different. For example, for F2t, we only have 1 parent, so its table will have only 2 rows. 1 row when F1t is true and 1 row when F1t is false. So this is how dynamic Bayesian networks work in practice. But let's also move a little bit to the theory behind dynamic Bayesian networks. They basically consist of, they are basically defined as a pair of G and theta. G is the structure or a graph that we showed here. It's a directed acyclic graph, and its vertices are the random variables. In our case, in our case, each node is a F delta. And the links between these nodes are the dependencies, failure dependencies. And yeah, then we come to the theta. And theta is the set of probabilities for each variable conditional to its parents only. And I already explained to you with this example. What is really beneficial for our cause in dynamic Bayesian network is what is a property called independence assumption. So according to this property, which I will explain better with an example, each variable is directly dependent on its parents, but they are independent of their non-descendants given these parents. So it's a complex good sentences, but what it says is, if I know the values of F3t and F2t minus 1, so the parents of this one, if I know the values of the parents, then I can assume that the failure probability of this node is independent from this one, because it's not a descendant of this node. I don't have to take into consideration all possible combination of nodes, but only the parents, which for this very small graph doesn't change much, but in a real dynamic Bayesian networks, the ones that we used in our research consisted of thousands of nodes. This makes a huge difference. You can just eliminate most of the probabilities, and you don't have to calculate each probability one by one. And if we want to compute now the failure probability of a deployment, we can simply sum out or eliminate some of the parameters by summing out their values. So S here is the servers that we use in our deployments. So what we need to do is to find the conditional probabilities of the servers that we take given the failure variable of their parents only. Not all possible servers, but only their parents. So if we go back to our example here, if we are interested in the probability that server 1 and server 2 fails at the same time. So these two, we are interested in these two nodes only. Then we need to calculate the probability containing these two nodes, of course, but also their parents, F1 and F2 in T minus 1. Oh, sorry, I showed the wrong nodes. The nodes we are interested on are F3 and F1, not F2. So we are interested in these two. So in our probability, we have these two plus their parents. So first benefit is, as I said before, we don't have to compute about this node anymore. The other benefit, we can simply sum the value of the values that we are not interested, the T minus 1s. And the good thing is, when we write this probability with the parents only, we can see that all these probability values are already available in our conditional probability tables. So conditional probability table is this one. and it already has the value of a certain failure given its parents. So what we need to do is simply sum out the probabilities that we already have in a table. So this is basic calculus after this point. And you can also use a more optimized way of calculation by a method called variable elimination. I will not go into that much into detail with this variable elimination, but at the end, instead of computing 2 to the power of delta nodes, you come up with 2 to the power of m computations, or q to the power of m time complexity. Here m is the longest parameter here. For this example, the longest parameter is this one, which contains 3 variables. So our computational complexity would be 2 to the power of 3. Of course, it doesn't make sense for this small example, but just to give an idea of what is the complexity in this case. So before moving to part 1, I would like to ask again if there are any questions. Because, by the way, this is the end of the mathematical and statistical part, so you can relax maybe after this point if it was too complex to follow. If there are no,
I think many people are really looking forward to see what's coming next.
Okay, great. Then let's move on. This part is about, so okay, we modeled our services, failure of our services. We modeled the dependencies between the nodes. But how can we learn these dependencies from data? So basically, how can we extract this graph given historical failure traces? And here I mentioned the graph because learning the graph is the difficult part, because then these tables, when you know this graph, learning these tables are not complex at all. Simply you count the number of occurrences, take the ratio. It's just basic calculus. But learning this graph in general usually made with expert knowledge. So someone knows the problem you have and they tell you these are the dependencies and you calculate the probabilities afterwards. In our case, there could be thousands of edge nodes, so there can't be an expert telling you that these could be dependent. Instead, you have to automatically extract this graph from data, which is an NP-hard problem actually, so you cannot find the optimum graph, but you can try to find a good enough representation of your data. And some further challenges here is that these failures have various characteristics, like their causes, their effects are different. As I said before, they are statistically dependent on each other, and these dependencies are dynamic. So you have to frequently learn this graph from scratch, or at least you can retrain using the current structure to optimize it. And then you have to do this optimization online, because the failure prediction should be in real time. When there is a service to be deployed, you cannot just say that, okay, after 1 hour, I will tell you what are the optimum locations, but you have to do it in near real time at least. So what we do to extract this graph from data is using a tool from literature, actually developed by Duke University in US, called Banjo. Banjo is a tool for Bayesian network inference, so learning these graphs from data. And it is score-based, so assigns a score to each graph and tries to maximize this score, or find the graph with the maximum score. It works for discrete variables. So your variables can't be continuous. You have to discretize them. In our case, this is not a problem because all our variables are binary. It runs a heuristic search. So it's not optimum. As I said, finding the optimum is an NPR problem. And it can output top n graphs by score, by their ratings. And it can also output a consensus graph of the top n graphs. And in terms of performance, it can run, it is parallelized, so it can do the search in multiple threads. And this is the general structure of the Banjo tool. It starts with a proposer. The proposer proposes a new network. Usually some kind of randomness is included here. So in a random way, it generates a graph. Then a graph or a network. I am again using these terms interchangeably. More specifically, they are networks. They are not graphs, but yeah. Then the cycle checker, as the name suggests, checks if there is a cycle, because we are looking for a duck, acyclic. It should be acyclic. Then there is an evaluator. As I said, this is a score-based algorithm, so it assigns a score to each graph. Specifically, it uses a score called BDE, which shows how well this graph represents your data. Then there is the decider module, which says, either keeps this graph or deletes it if it is not good enough. And we go back to the proposer again to start with either new graph or a modification of the graph we already have. So the exercise part that I have mentioned earlier would be based on this tool. We will use this tool for a simple learning problem. That's why before having a break, I will give you some preliminaries that if you are interested in doing yourself during this tutorial, you can also follow these preliminaries. I will leave it on the screen to download necessary packages. There is not much to download actually. So if you want to follow along, as I said, I will do it on my screen. If you want, you can try yourself, or you can try later as well. And I will post these links to the chat as well. So one thing you need is, of course, the Banjo tool. It is from the website of the Duke University, and you have to register or fill in a form, basically, to declare that you are downloading it for non-commercial purposes. And yeah, then they will send it a link to your email address and you can download it. It works with Java, so you need to install Java runtime environment on your computer. Then you can test that it works with this command. So basically, Java command, you are running a jar file, you will download it from here. The name of the file is Banjo jar. And if you run this command, Banjo will run, but it will give you an error message because you have to declare a configuration file. So it will say configuration file is not found, but it shows that it is working. So you can test it this way. And I provided some example data set and an example configuration file in this GitHub repository. There is only 2 files on this link. You can also download these to your computer if you want to follow along. So we already passed 1 hour mark. So I would say maybe we can have a break of at least 20 minutes. Alessandro, if that is also fine with you.
Yes, totally. We can have a 20 minutes break, so we start at 10 past.
Yeah, perfect. Yeah, so as I said, I will put this link to the chat now, in case you want to access them.
So I will pause now the recording.
Mm-hmm.
So welcome back everyone to the tutorial on fog computing for IoT. So we have again Atakan that will continue with his part of the tutorial.
Hello and welcome again. Yeah, if you would like to follow along, as I said, I will do some practical parts now. And for this, we need the Banjo framework or Banjo software and Java runtime environments and 2 configuration and dataset files that I shared in my GitHub file. So probably you see my desktop now with several several folders open. Okay. I hope the font size is good enough for readability. So
yeah, it is readable on my screen at least.
Okay, great. When you download the software, you will have a zip file and you can extract it. You will have these files on a folder. Now it is on my desktop. The folder is called Banjo 2.2.0. And the most important file is this jar file inside the folder. Other than that, there is the data folder, and we are working with release 2, and it's arbitrary, but let's go on the dynamic part. And the configuration files that I sent you, one of them is esw.settings txt, and inside this file should be like this. And you can put this file here in the folder dynamic. Actually, you can put it anywhere. When you run the code, you just need to give the path to this file. So in my example, it will be in this folder called dynamic inside release 2, and that is inside data. So data, release 2, dynamic. I put the configuration file here. And in the same folder, there is another folder called input. And in this folder, you can put the dataset instead. And dataset should be looking like this one. And this is the failure dataset, albeit very small example of it, but for better understandability, I think it fits better.
A question, the data, are they like separated with the tab, or is it like a bunch of spaces?
It's tabs, but I'm not sure if spaces might also be working. I'm not sure if it differentiates between them. In the file that I shared with you should be working directly. So we have the configuration file in the dynamic folder, and inside that, in the input folder, we have the file. So let's go to the configuration file first. So ESW settings. And I will go through all parameters later on. But for now, we would only change the input directory. If you use the same folders as me, you don't need to change anything. Then the name of the observation file. Again, if you use the same folder, if you didn't change the name of the file, it should be already correct. So we tell Banjo to use this input file for running the algorithm. And then we have here a terminal whatever operating system you're using, a console or terminal would work. So what you have to write is Java -jar banjo-rar. So this is a classical way of running a jar file. Please ignore these prefixes in my terminal. I didn't set up the paths, that's why I have to put these. So normally this should be enough. And then, if you run this, you will get an error because you should also specify the settings file. And I set the settings file in the relative paths because banjo jar is here. So I put the relative path data release 2.0 dynamic ESW settings.txt. So it will read this setting file, and in turn, it will read this data set, and of course the parameters as well. As I said, I will go over these parameters later, and it will run the file when I execute this command, hopefully. It always errors happens in live systems, but let's see. So it will take 30 seconds because here in the configuration file, I set maximum time as 30 seconds. For this kind of small exercise, even 1 second is enough, but yeah, I leave it like this. You don't need to give it so much time. So in 30 seconds, actually in 20 seconds, it already searched for 80 million graphs. Actually, we don't have 80 million possibilities at the moment, but still. So the file, it finished, and let's go to the beginning. Search statistics, yes, final reports. Anyway, we don't need to check the result now. It doesn't matter. What we need to do is to go to the output folder now, because here we set the output directory to that folder, and the output file is this report file. But for now, we will not go into the report, but to this graph point top file. So if you open this, it is a file that represents a graph, the best graph that Banjo has identified. And to visualize this, by the way, normally Banjo automatically creates a JPEG file as well, or PNG file as well from this graph, but you need to install a specific software for it. And if you didn't install it, it will just give you an error like this. The attempted execution of that to create graphics file did not succeed. But it doesn't matter because we have the graph. And if you copy this, and if in your computer, if you have GraphViz installed, you can directly visualize this. If you don't have, there is an online service called Editor. So not editor, but with dot files, because the format of file is dot. In editor.net, you can just paste the graph and it will just visualize it for you. So what does all this mean? We inputted a file with 5 columns, which means we have 5 variables, and each line is an observation. And as I said, we have binary values. In our case, 0 means no failure, 1 means failure. And it identified some dependencies between different variables, but we will talk why specifically these dependencies are suggested in a little bit.
Question,
yes.
Why, is there any reason why there is no node number 2?
Yes, there is a reason, and I will tell you about this.
Okay, thanks.
So before going there, let's check our settings file. This is a minimal setting file. This is the minimum parameters you have to give. In the Banjo folder, there is in the input, there is another one which is more detailed. Sorry, not in the input, but configuration here, dynamic settings with comments explaining what each parameter is you can check all the parameters here. We can also go through soon, but for now, let's check the mandatory parameters. First, you have to tell Banjo which kind of searcher it should use. So how should it search for new graphs? And here we're using simulated annealing, which is a heuristic method for optimization. Then you should tell it what kind of proposer it should use. Proposer means when you have a graph, how you generate new graphs and how you move to the new graphs. And all local moves means all possible extension from these graphs. So an extension can be adding a link or adding a vertex. Actually, you already have the vertex, but so adding a link or removing a link is a move. So when you choose all local moves, you move to all possible directions and try all possible different movements at each step. You can also choose the best move. I forgot the abbreviation for it, but in this case, it only moves to the best one. And then you can also combine it with a searcher, with a greedy searcher. You can write here greedy, then it will always move to the best node and it will always greedily try to find the optimum. And of course, this is not a good way of optimizing something because you will get stuck in local optima. Sorry, just a correction. There is all local moves and there is random move. There is no best move. So it doesn't go to the best one. It goes to a random one or all possible ones. And if you combine all possible ones with greedy, you will always move to the best neighbor. It will have the better score. So in this case, as I said, there is a risk of being caught at local optima. But anyway, these are available possibilities. For in our work, we used simulated annealing and all local moves option. Then you should tell the directory of the input file and the name of the input file, then the directory of the output file and the name of the output file. You should be careful that when I run this code again, it will not write over this file, but it will append to this file. So at the end, it will add the new report. So you might get confused as if the report doesn't change. The same goes for the graph. It will append to the end a new graph. Then the next parameters, you should tell it how many variables you have. I don't know why it asks this because it can check it from the file. It is 5. And if you give anything other than 5, it will give you an error. Let's try with 4. If you run the same code, you will get the error, end of error. And here is the error. Number of variables specified in the setting file 4 differs from the number of variables found in the observation 5 columns. So it already knows it is 5 columns, so I don't know why it asks me what is the variable count. Anyway, maybe it's a double check not to make mistakes. So this variable count should be the same as the number of columns you have in your file. Then Markov lag is a property of dynamic Bayesian networks. It tells me how many historical steps should it take into consideration when calculating the dependencies. Right now, I put 0, which means I'm not searching for a dynamic Bayesian network, but a regular Bayesian network. So there is no time information. That means I can only detect dependencies in the same time step. If I change it to 1, then it means I can only take the dependencies from one time step before. And if I put to 0, minimum 0 and maximum 1, then that means I check both of them, both in the same time step and in the previous step. And in our case, this makes the most sense because we are looking for both 2 types of dependencies, as I explained before, simultaneous dependencies and also dependencies where one is the cause and other is the effect. But instead of 1, you can also go 2, 3, whatever value historically you want to go. Of course, this will increase the search space immensely. So we will go for 1 maximum in this example. But when you have time, you can run it for higher values as well. Yeah, we can skip these parameters. Here you basically say at the end of the algorithm run, how many best networks do you want to display? 5 best can be done. And they should be non-identical because we don't want the same graph twice, because it is possible. Because you are randomly searching, you can be reaching the same graph twice. So we want the non-identical one, and we also want the pruned graphs. And then you put some parameters regarding how long the search should continue, because the longer you try, the more graphs you explore, and there is a possibility that you get a better results. Of course, it's not guaranteed. It could be the case that you get the optimum result in the first trial because it's a randomized algorithm. But of course, the more time you give it, it is possible to have better solutions. For now, I will put it 30 seconds. As I said, this is more than enough for a very small graph like this. A few seconds is enough normally, but you can also limit not in terms of maximum time, but other parameters. For example, how many simulated annealings should be done, or how many restarts, or how many networks should be explored, and so on. There are different parameters to put a limit to your optimization. Then you can put a limit of maximum parents in your graph. So 2 means each variable can have 0 parents, 1 parents, or maximum 2 parents, and not more. If you increase this, again, the search space will increase, and it will take longer to find an acceptable output. And finally, this parameter is for creating this file. If you don't put this configuration, it will not create the graph file. And it always creates the graph file for the best ranked network. We are asking for here 5 best networks, and among them only 1 is the best, and it creates the dot output for this file. So let's look into our data set and also our graph now, because we run it for 0 Markov lag, which means we check only the dependencies in the same timestamp. So this is 1 timestamp. So at this step, only number 3 fails, and all others are active. And in the next one, the others have failed, and node 2, the other all fails, and node 2 is available. And it goes like this. And if you realize the pattern here in this file, node 0, node 1, node 3, and node 4 are exactly the same. And node 2 instead is completely different. Yeah, except in some steps there are full zeros, but in other ways, in other steps, there is no similarity to that one. That's why when we train our dynamic Bayesian network, or we extract the structure for the dynamic Bayesian network, it finds all the dependencies between 1, 0, 1, 3, and 4, but 2 is not included because there is no dependency to 2. 2 is not dependent to anything, and nothing depends on 2 as well. So we could have something similar to a complete graph here. Almost everything is dependent on everything, but we cannot have a complete graph because we put a limit on maximum parents. We put a limit on 2. And you might also notice that there is a cycle here. Normally the graphs should be acyclic, but I don't know if this is a bug in the code, or maybe it doesn't count this kind of one-legged cycles as cycle. I don't know, because you can also visualize this as a two-sided arrow, and in this case there is no cycle, probably. Yeah, maybe this is the reason this was allowed, but normally this graph should be acyclic.
Could it be related to the fact that you have two parent nodes, and then 3 is considered parent only for that edge that goes from 3 to 0?
So
maybe.
Do you mean for the cycle check?
Yeah, I mean, I'm thinking you said the max parent count to 2.
Yes.
And one parent is definitely 1.
Mm-hmm.
And the other one could be 3.
Yes.
But then if you consider the edges going out from 3, it's only that one that creates the cycle. But then it is not detected because probably the cycle detection is done over a single, starting from a single parent and then going forward.
Yeah, that could be it. Yeah. It doesn't check again. Yeah, maybe that's the reason. Yeah,
maybe I'm just guessing here.
Yeah. I also don't know, but this doesn't cause any problems because, as I said, in this case where there is no Markov leg, the dependency directions are not that important. So these two arrows mean the same thing actually, because they are in the same time step. That means it doesn't matter which one is the cause and which one is the effect, because they happen simultaneously.
Yeah.
So let's change our file a little bit, and this time check only for dependencies in one time step difference. So here there is something interesting in the file that I sent you. So in the first time step, node 2 fails, and the next time step immediately all other fails. Then again here this one fails, and in the next one all other fails. This one fails, and in the next one all other fails. So it's obvious that all others are depending on node 2, because a failure on node 2 always causes, of course this could be coincidence because we have a very small file, but it will detect this kind of coincidences here, because a failure always follows one step after, and we are checking only one step after, and it will detect this dependency. So what we expect is node 2, so all others will depend on node 2. So let's try. Did I save this file? Now saved, and I am running it again. And we will wait 30 seconds. And if you run it for a longer time, it always gives you periodic updates. Like every minute it tells you, this is the graph I found until this point, and its score is this. Even now it tells me how many renewals it makes, how many networks it already explores. But after certain periods, it also gives you more information. So the execution has been completed. If we open the graph file, as I said before, it didn't overwrite the first graph, but appended the next graph. So you have to copy only this one, go to the Ethernet or any visualization tool that you have, and as expected, all nodes depend to 2 now. The dependency detection resulted as we expected. There is another backwards loop here. Again, I don't know the reason of this, because the method is randomized. If you try again, maybe you will have another dependency, but as I said, there is a probabilistic part, so it's not the optimum solution always. You get
a question,
but it's good enough. Yes, please.
How easy is to seed the randomized algorithm?
What do you mean, see?
seed, meaning like using a seed for the randomization, so that, for example, if I run this twice, I will get the same result for reproducibility reasons.
I didn't check, but maybe in the configuration file there is something about the seed. Let's search for seed basically, and if we get something. No, but Banjo has a very detailed documentation.
Okay, thanks.
Yeah, when you download it, you will have it here. There is one for user and one for developers. And I'm sure they talk about what kind of seed they are using and how can you change it. And since we are here, I will also tell you about the developer option, because I am now using this console to show you the results. But of course, normally you can integrate Banjo using the developer options to your code. So you can, for example, run it in a simulator and try different configurations automatically, which is what we did basically. So of course you don't go to console and try different configuration manually, in a normal way. Let's go back to the data, release to dynamic. Did I visualize it? Yes, it came as we expected. Then a third option could be giving minimum Markov leg of 0 and maximum of 1. So it will try 0 and 1, both of them, and then try to create a graph for this. And it will also label the nodes so that I can know a dependency is for the same time step or for different time steps. You will see. And you can also play along with parent count. You can try different configuration, different algorithms, and see. Probably for this very small graph, it will always give the same result, because in 30 seconds, I am sure it is exhausting all possibilities almost. So, but for larger graphs, you can have different results in every trial. So it's done. We go again to output folder where the graph file is here. So you have to close it and open again so that it is updated. The third graph is here. If you notice, this time it is labeled with lag values, lag 0 or lag 1. Let's copy this to our visualization tool. And yes, so what we see here is basically in lag 0, in the same time step, the nodes are connected to each other, 1, 3, 4, and 0, somehow connected, all of them. But in the same time step, because they are basically the same, but in different time steps, in different time steps, for example, a failure in time step 0 at node 2 affects a failure at node 0 at time step 1. So this dependency is enough to represent, because it means 2 depends on 0 and 0 depends on all others. That means 2 also depends on all others. Or yeah, so it is this kind of this is the minimalized minimum representation of the difference dependencies that we have. So it would not change anything if we had here node 1 instead of 0. And one of them would be sufficient. Does anyone have a question until this point?
As you saw, I'm trying to interrupt whenever I have a question, so feel free to interrupt Atakan every time you have anything.
Yes. Okay. Then let's try something more realistic, a larger file to see a better, more interesting graph, maybe. So to do this, there is already an input file that comes with Banjo that is called dynamic.data.txt. So what you need to do is to basically change ESW to dynamic, and then it will read this file. And this file has several columns. It says, yeah, 20 columns, so 20 variables and 2000 observations. It is still a small file. What we worked with was hundreds of thousands observation and thousands of variables. So still small, but manageable. Then we have to say that there are 20 variables. Let's remove the lag for now, so the graph is easier to read. But let's increase the parent count to, I don't know, 5. And give it at least 1 minute, so you will get better results. And save it and run our code. After this execution is finished, we can take a look in the all settings, more settings. What do they mean and how do they work? So in 30 seconds, it's already explained 17 million graphs, now 24 million graphs. Of course, this depends on which machine you are running and how many threads are you running with. So when you run your code, you can simply give another parameter, threads equals 4, and then it will run in 4 threads. It is as simple as this. So the execution is completed, and we can check the output file. There is a graph there. After I close and open again, the graph is here. Let's copy it, paste to our visualization tool. And yeah, this is a type of graph that it can detect automatically from file. And as we increase the number of allowed parents, we get more complex graph, of course. And as you see, there is a score under the graph, and this shows how well it is always negative, by the way, but of course values closer to 0 are better. So this value represents how well this graph represents our data, how well it fits. And of course, you can in Banjo you can implement your own searcher, your own proposer, your own cycle detector, or even your own score. You can choose to use a different score, and it optimizes based on that score. So let's check the configuration file one more time in more detail this time, because as I said, this one was minimum required parameters, but there are other parameters. Let's zoom in. Yes. So you can give a name to your project, which will be shown here. Other than that, it doesn't change anything. And nodes, user, etc. These we already talked about, input and output files. variable count we already talked about. What you can do is, if you already have a solution, for example, you already run your algorithm offline and you have a good enough graph, but in the runtime you want to, maybe something has changed, so you want to rerun your algorithm, but you don't want to rerun it from scratch. In this case, you can give it an initial structure file, basically the output of this graph. And in this way, it will start from this file, but try to find something better. Maybe it will return the same file or same graph, but it is the starting point, which reduces the search time dramatically, of course. You might also choose that these edges or links have to be in the file, because, for example, maybe you already know there are some dependencies exist, because you know maybe you know that these two nodes have the same network, so they have to be dependent. So you can tell that this edge must be in the file. Or you can also say which edges should not be, definitely not in the network, and it will just skip them. And this way you can reduce your search space. If your inputs are not discrete, but continuous values, you can use a discretization policy. There are some exceptions and whatever, not really related. Then, as I said, there are 5 modules: searcher, proposer, evaluator, decider. Actually, there are 4 modules, and there is a statistic part as well. For the searcher, you can choose greedy or simulated annealing, or you can implement your own searcher. For proposer, there can be all local moves or random move. Evaluator and decider, there is only one implementation that comes natively, but as I said, you can implement your own if you want. Then there is this Markov lag parameters. There is maximum parent count that we already talked about. This is just visualization things, how frequently the screen report should be given, and then how frequently the file should be updated. So every 10 minutes you can update the file to see the intermediate outputs. And what would be your stopping criteria? And it will stop as soon as at least one of these criteria is satisfied. So it will, in this case, it will stop when 10 minutes mark is reached. But you can also put here 1 million proposed networks. That means it will stop when it searches for 1 million networks, or when 10 minutes has passed. Any of them is enough. Or you can tell after how many restarts it should stop as well. Then there are parameters for specific algorithms. As I said, there are 2 algorithms. We used simulated annealing. For simulated annealing, there is initial temperature, cooling factor, and so on, typical simulated annealing parameters. For greedy, there are also other parameters: when it should restart, after how many networks it should start from 0, so that you are not stuck in local optima. Yeah, then you can choose to display memory info and display structures or not. These are the most of the configuration parameters. There are even others in the documentation that you can check. But let's check the output report now. For now, we didn't check the output report. By the way, the report is same as what is displayed in the console. So I didn't go through what is in the console, but it is the same as this report. So you didn't miss anything. Zoom in, yes. So in the beginning, it tells you again your configuration. We already talked about the configuration, so we can skip it. But here you see that the default for evaluator is evaluator BDE. This is the score that I mentioned that is always negative, and it shows how well your network represents the data. And for the decider, it uses Metropolis, which is the default one. Yeah, the parameters that we already set. Then the output starts. Yeah, we had 3 intermediate reports because it ran for 30 seconds. By the way, we are reading the report of our first trial now, because as I said before, all reports are appended to each other. So this is our first report. That's why it is 30 seconds. So we already saw this information in our screen, so we can move. We told it to give us 5 best networks. So we see here, I don't know why, but we see 4. 4 of them were non-equivalent. Okay, it finds 5 best networks, but 2 of them were the same. So it's reported 4 non-equivalent ones. Okay. These are the networks, and the best one is this one because it has the score closest to 0. Then, yeah, there are some statistics collected during the search. How many links were added, how many links were deleted, and how many links were reversed. So the direction has changed to find a better solution. How many nodes are with no parents, how many are with 1 parent, how many with 2 parents, and so on. Then again, we see our networks. There is also post-processing. In the post-processing, you can tell it to find a consensus graph of these 4 graphs. So it combines them in a way that represents a combined fused network. And this is the best network, network number 1 in GraphViz format for visualization. And final checkpoints, and that's it. This is the end of the report. Here starts the next report, and we run, I think, at least 4 times, so we will have 4 reports here. Okay, does the audience have questions about the way we configured it and how we get the results?
Everything seems quite straightforward. Of course, when you do it and you know what you're doing, it's always
yeah, it's always a little bit try and error, because you don't know, especially these heuristic parameters, you don't know what will work good. You think sometimes something will work, but then when you try it, you get caught to the local optima, so it doesn't work well at all. So you have to try different parameters to be able to get a good solution. Of course, if you are a researcher in machine learning, you are probably knowing what you are doing better than me. But in my case, I just tried different configuration and find the one that works best for the problem that we have.
So, I mean, knowing a bit about machine learning, what I would say is that it should be a bit combination of, for example, increasing the max time parameter that, of course, improves the possibility of finding the global optimum, and having multiple starts with different randomizations, and that somehow could be controlled with the seed. But I mean, even if you don't have control of the seed, just running it multiple times then could do the job. And then in principle, the optimal one will be the one that is the best out of all the multiple runs.
Yeah, exactly. Yeah. Okay. If there are no other questions, maybe we could have another short break so that I prepare for the rest of my presentation. To give a sneak peek, I will talk about, so now we know how to calculate these dependencies, but how do we use this information? How does it benefit to us? And to be able to, we can use this information to deploy our services in a way that they are fault tolerant. And I will give you two algorithms for this purpose after the break.
Okay, how long will the break be?
Maybe 10 minutes is enough.
Yeah, okay, so we start at 8:05 Central European Time. So we start again the session, the last part. So Atakan, the stage is again yours.
Thank you, Alessandro, and welcome everyone, and thank you for remaining until this late hour, I would say, but depending on where you live. So as I said, we will continue with some algorithms to use all the information that we have collected previously. So let's go back to our overview graph or our overview diagram. Sorry. Okay, my pointer was not working for a moment. So what we have talked about until now was dependency learning, where we used the failure traces to extract dependencies. And also we talked about how can we calculate the failure probabilities from this Bayesian network. So we did it from kind of inverse order. We first talked about this because this is more mathematical parts. Then we talked about this, where a machine learning algorithm software called Banjo was involved. So these parts are already covered. And now, since we can calculate the failure probability, how can we use this information to for resilient edge computing services? So just to remind you again, the process starts with the service provider who provides the requirements to the algorithms. The algorithms then come up with some candidate deployment according to these requirements and sends them to the inference module, which calculates the failure probability and sends it back to the resilience algorithms. It can do multiple iterations to find a better deployment. And when the deployment is good enough, it is sent to the user. And our goal here is not to give the best algorithms. We just want to show that this kind of dependency learning approach works. That's why the algorithms that I will present you are quite simple. They simply find the optimum solution via brute force. And the reason for this is that first we want to show the maximum benefit of dependency learning. What is the maximum amount of resilience we can have? This is the first reason. And second, in practice, you never use resilience algorithms alone for your deployment, because there are many factors involved in the deployment: where your user are located, where is the low latency, where is the computational capacity available, or how much energy this edge computing deployment would consume. You have to consider many other parameters. So it doesn't make sense to come up with a algorithm that finds the deployment only considering reliability. That's why we are now going on with two theoretical algorithms, but in reality, this failure probability information would used in combination with other parameters. And if we have time, end of this presentation, I will also show you a way of doing it, combining it with other parameters. Anyway, so there are two algorithms that, as I said, find the optimal solution. First one finds the optimum in terms of failure probability. So it finds the deployment with the minimum failure probability, such that the size of this deployment is M. This works when the service provider has a specific budget. So there is a limit how many replicas it can deploy, M. So it tells that, for example, 10, find me 10 locations such that their joint failure probability is minimum. So this is what this algorithm does. The other, let's say a dual version of this algorithm, again, finds the deployment with the minimum size this time, and subject to failure probability would be under some limit P. So, and this also makes sense when you want to achieve some kind of availability, but you want to do it with minimum number of replicas, of course. You don't want to deploy unnecessary replicas if you already satisfy the availability requirement. So yeah, this is the second algorithm, and both algorithms have an input. This one has an input M, and this one has an input P. So if we go to these algorithms, as I said, I will not go much into detail of these two algorithms. The one on the left is the optimized joint failure probability. Its inputs are currently available servers, because some of them could be already offline, so we don't consider them. Another input is the initial copy, and so we can replicate it in multiple locations. And the third input is how many copies we will deploy. So what it does basically is very brute force. It finds all subsets of size M of the available servers and evaluates each one of them. So it's extremely complex. But as I said, our point is not to provide an algorithm that would be used in practice, because it wouldn't make sense. An algorithm that considers only reliability wouldn't be used in practice. So we only implemented an optimal algorithm. And the second algorithm is optimized size. First two inputs are the same. The third input is what is the maximum acceptable failure probability. So we will find a deployment that has a joint failure probability less than P. And what it does is to start with a deployment size M1 and calls the optimized joint failure probability algorithm. So it finds the solution with one deployment with the maximum availability. If this value already satisfies the condition, then we return this solution. Otherwise, we increase M by 1 and try for 2 deployments. And if we find the optimum solution, not optimum, but acceptable solution, return it. Otherwise, increase to 3 and so on. So in this way, we will find the deployment with the minimum size. Again, this algorithm is brute force, and in practice, it's not possible to use it. But our goal is to show the maximum possible improvements. So I already described all the modules to you, all 3 modules. And now I am interested in how can we verify this approach works? How can I say that it is an improvement to an algorithm that doesn't consider reliability at all, or an algorithm that considers reliability, but not the dependencies? For example, you can also check the individual failure probability of each node and then choose the lowest probability ones without considering the interdependencies at all. And this is also a solution. but how much additional value our approach brings. We are interested in this knowledge. And a challenge here is that there is no cloud computing reliability data set. This is the first thing. And the second thing is there is also no fixed deployment for cloud, edge computing. I'm talking about edge computing. There is no edge computing reliability data set, and there is no large-scale real-world deployment of edge computing as well. And there are different configurations proposed by different people. For example, one of the previous speakers mentioned that when they say edge, they mean network edge, which is common for network researcher, but other people may mean edge as the client devices. So, there is fog computing, which uses the whole continuum, and there are different ways of doing this, and these would have different availabilities. So what we did was to take 3 representative cases, one using client devices. So we used the failure traces from client devices. The other one is having a setup box in business premises as an edge computing node. And the third one is using the networking hardware, for example, gateways or DNS servers as edge computing nodes for computation. So these 3 types of edge computing have different benefits and drawbacks. Of course, using the client device minimizes the latency, so our round trip time is minimum, but it also has the lowest availability. So if you are using a client device to offload your computation, you should consider that it can go offline anytime. So on average, in this data set, availability was 44%. And only 4% of the servers, these are not servers, devices, but let's call them nodes, only 4% of the nodes achieved an availability higher than 95%. This is very low because our aim is to find a deployment comparable to cloud. So we need 4 nines, so 99.99 availability to be comparable with cloud, at least. And the next one is business premises with average availability of 64%. And in this case, we are a little bit better because now 35% of the nodes have greater than 95% availability. This is better. And the last case, using the networking hardware, which is much more reliable, on average, we have 91% availability, and 85% of the server has greater than 95% availability, which is quite acceptable. So we want to see how much improvement we can get in all these different cases. There are also differences between computational power. When you use client devices, you have the minimum computational power. Then in business premises, you can have a stronger device or a server. In networking hardware, you can have even stronger computer or a server. And this one shows the detailed distribution of these of the availabilities in these data sets. So which percentage of the servers in a logarithmic scale has what kind of availability. So here the red one is, as you see, it peaks here. So most of the servers, almost 90 something of servers have a very high level of availability. The complete different is the green one, where 10% of the servers are even never available. This is a case, and the rest is also uniformly, more or less uniformly distributed. And we have in the middle the blue data sets for Skype data set, where it is a middle way in between these two solutions. So using these three data sets, we run a simulation that integrates the Banjo framework as well. So we train graphs, networks, the dynamic Bayesian networks from all three data sets, and also use these data sets as the workload. So half of the data set is used for training, the other half was used for traces for the evaluation. And we created random tasks of requiring 1 to 5 copies, and they could be load sharing replication or active standby replication. We selected 10 disjoint sets of 100 random servers from each data set, and we run our experiment for this. We repeated our experiments 10 times for this subset of random servers. So in the runtime, we decided about the available servers based on, as I said, the second of the failure traces. Sorry. And yeah, I already said this. First half is for learning, the rest is for simulation. We use the Markov lag minimum 0, maximum 1. We tried also higher values of Markov lag that didn't bring any improvements or significant improvements. In result, the training time increased exponentially, so we stick to 0, 1. And to evaluate, we compared deployments again to real future traces. So we predicted failure, and then we checked the real future state if it fails actually in the future or not, and then used this information to calculate our metrics. And our first metric was, did I miss something here? No. Our first metric was service downtime, which is a typical metric for reliability. So what percentage of the time the service was offline on average? And we evaluate this with different lengths of tasks. So for very short tasks, it is easier to make predictions because you already have the most recent data, and it is unlikely that it will change immediately. But as the task length increases, then you are making a prediction further into the future, so your accuracy drops a little. And we didn't retrain in this experiment. So we use the same DBN from the beginning and until in all configurations. And you see here 4 different results for 4 different algorithms. One is optimized joint failure probability, or optimal solution. I mean, it's optimal based on the Bayesian network that we have, but Bayesian network itself is not optimal, so we cannot actually say it is optimal, but it is optimal based on the information available to us only. So this algorithm considers, of course, it considers failures, and it considers the temporal dependencies between failures and also spatial dependencies between failures. So spatial dependency means dependency between 2 different nodes, and temporal means also 2 different nodes, but in different timestamps. So our algorithm considers all 3 of these. The second baseline, or the first baseline, is TTF, which stands for time to failure. This is from the literature, and it uses again a machine learning approach called support vector machines to predict future failures. This can be said that it is the state of the art until our paper. And it, of course, also considers the failures, and it also considers temporal failures. Maybe there is a mistake here because it considers spatial failures, but not temporal failures, probably. Yeah. Yeah, and the temporal aspect is missing here. Then we have the prior algorithm. Prior algorithm is a simple algorithm which assumes that if a server was 90% of the time available before, it just assumes that in the future its failure probability is 90%. So nothing will change. So it doesn't consider the dependencies as well, and but it considers availability, at least in a basic way. And then we have random placement to see the net benefits. So it doesn't consider failures at all. And as you can see in LDNS dataset with the highest availability, our system, our algorithm managed to very high level of availability, almost 0%. And in the case of the middle ground algorithm, again, the availability was quite low, and the other algorithms, for example, random, even had 4% downtime, which is not acceptable in a realistic setting. And but the best performing algorithm, TTF, also started quite well, but then almost reached 2%. In the most unreliable data sets, on the other hand, for short-term tasks, it was still okay, around 1 to 2%. But then for longer tasks, the predictions became more and more inaccurate, and we reached almost 10% downtime, which is, again, not acceptable. And in this longer tasks, TTF also performed slightly better than our approach. But yeah, both values are unacceptable anyway. So this tells us that if your environment is very unreliable, then you have to rely on retraining your algorithm, because for longer tasks you will have worse results. By the way, if you check the indexes here, if you check the x-axis in 3 graphs, here you can see that we tested much longer tasks, up to 100 hours. Here we have only 10 hours. That's why the performance drops. That's bad in this case, because this third data set was much larger than the other ones, so we were able to test longer task size. Okay, this one tells us that our algorithm finds good deployments, but we still don't know if it finds this deployment because of dependencies, or it just finds good servers, no matter the dependencies. So to better understand the inner working, we checked another metric called loss of redundancy. So we define loss of redundancy as the case where a failure happens, one of the server fails, but the whole general service is still available. So it can, if it is, for example, active replication, you lose one of the servers, but others are still active. So your system, your service is still available. What is interesting here is that here you can see our algorithm actually has more loss of redundancy than TTF algorithm. The same here. It has the loss of redundancy. Higher loss of redundancy. But if I go back to the previous results, overall downtime was lower. which means the deployments that we propose can tolerate loss of redundancy better than other algorithms. So even if some failures happens, they can tolerate this kind of failures. In the Skype dataset, on the other hand, our algorithm also finds the lowest loss of redundancy. The reason for that is that this Skype dataset is very heterogeneous. There are servers with very low availability, and there are servers with very high availability. So here it is more important to find, to detect highly available servers, and our algorithm manages that, and then the downtime is lower. But in other cases, dependencies gain more importance. So you don't have to use the most available server, but you should find a subset with the lowest failure probability, not individually lowest one. This is also better for utilization of the resources, because then if everyone uses these algorithms, then and they only choose the most available ones, then there will be competition and the price will increase in an open market edge computing deployment, for example. But our algorithm also makes use of less available servers, but at the end the service is more available because they are not dependent on each other and they don't fail at the same time. So this is a interesting benefit for us. Then we move to a more practical metric, that is how many times was the SLA violated, and we used a very strict level of availability, a very strict SLA, which requires 99.99 availability. And in whole simulation, where for each data set we run 10,000 requests, only 5 times the SLA was violated in the case of LDNS, 700 times in the case of Skype, and as you can see, much better than the baseline algorithms, and around 3,000 times in SETI. 3,000 is still quite high because out of 10,000 requests, 3,000 of them dissatisfy the SLA. But yeah, as I said, this is also partly because the task length is very long in this case. So we are evaluating very long prediction for a very long time into the future. In reality, we have to train a new Bayesian network so that the performance doesn't get that worse in the long time. So until this point, we only evaluated one of our proposed algorithm, which optimizes the failure probability. So what about cost? So which is about the number of deployments. So we also run a cost performance analysis, where I only show you the results for the 2 data set, because the third one, LDNS, which uses the network hardware, the availability is already very good in this case, so it is not possible to find a trade-off there. It performs the best, but there is no trade-off at all. But in these 2 cases, there is an interesting trade-off. And what we analyze, as you remember, this algorithm that we called optimized size takes a parameter P, which is the acceptable level of failure probability. So we evaluate it with different values of P. So if we choose a very small value of P, then it needs a lot of copies to satisfy this requirement. So number of copies were quite high in this case. But if you increase your tolerance or decrease your tolerance, if you get less strict, and if you accept, for example, 0.05 probability of failures, then you can do it with, oops, sorry, this red line is the number of copies. You can do it with much less number of copies. Then at the same time, of course, downtime increases. If you tolerate more probability, then your downtime would be higher. And these lines are the best baseline, which is the TTF algorithm that uses support vector machines. And this algorithm, of course, is independent from this p-value because p is an input to our algorithm. It is independent from TTF. So its performance in terms of downtime is this line, this dashed line, and its performance in terms of copies is this line. And what these results show us that, I will not go through this second graph because it's the same actually, but these two graphs tell us that in all 300 different configurations that we tried for in terms of failure probability and number of copies, in every case, our solution was non-dominated. So non-dominated means it achieves either less copies and the same downtime, or less downtime with the same number of copies. So it was better in one way or another. Moreover, it also achieved a stronger performance in these highlighted areas, in shaded regions, where it is Pareto dominant. Not only non-dominated, but it was also Pareto dominant in these shaded areas because it has both less number of copies and also lower downtime. For example, let's consider this case of 0.02. In this case, blue point is less than TTF, so it has lower downtime. But also this red point is less, so it deploys less copies. So it manages to have better availability with less copies, which is a very strong property for this kind of algorithms. So I want to repeat again, these algorithms that I explain here are the optimum cases. So they are the maximum benefit we can get from this approach. But in reality, of course, the benefit could be lower. Yeah, so this is the end of the parts that I explain evaluation, but I don't think it will make sense to move to the next part because then I will be over my time. That's why I will move instead to the conclusions. I just summarized 3 takeaway messages from this tutorial. The first one is that we showed that spatio-temporal dependencies affect failure resilience significantly because our algorithms had higher loss of redundancy, but they still manage lower SLA violations and downtime. The second message is that the proposed dependency mining approach is able to capture these dependencies in an accurate way, at least in the offline setting. And the third outcome is that it is possible to have availability levels comparable to the cloud, despite we are using very unreliable resources and we are having fewer copies that we can have in a cloud data center. So this brings me to the end of my talk. I would like to thank everyone who remained for their attention in this late time. and this very long, at the end of this very long tutorial.
So thank you, Atakan, very much for the very interesting hands-on part. It was a nice combination of some practical and more theoretical insight on your work. And I believe that all of us really appreciated what you presented. So thank you very much. I mean, it's going to be a virtual applause, at least from my side, but thanks very much. There is time for some questions if you want. Otherwise, we can move to the conclusion of this tutorial. Is there any question for Atakan? If not, then I would say that yeah, we can wrap up very quickly this tutorial. So we have been talking about several different topics today, and I hope that you enjoyed all of it. We ranged different aspects from theoretical to practical. So if you have any question related to all the presentations that you have attended, or if you have any problem, for example, with some of the things that Atakan presented, and maybe you don't manage to make it work as smoothly as he did today, so maybe you can contact either me, and then I will try to forward your request to the proper email address, or directly to the authors. So with this, I thank you all very much for attending, and I wish you a very good weekend.
Thank you also for the smooth moderation, Alessandro. It was a good tutorial. Thank you.
You're welcome. There is actually one person, Zainab, that raised her hand.
Hello again, Alessandro.
Yeah, no problem.
Thank you, Atakan, for the very good presentation, but I unfortunately missed some part of the tutorial. So, and I heard that you said you will have like a recording. Is it like you will upload it somewhere and we can access it, or?
Yes. So as you have seen during the overall tutorial, the tutorial was recorded, apart from the first presentation that was given by Wilfried Steiner. That was not recorded, so unfortunately you will miss that. If you miss that, then it's gone. But all the rest is recorded, and it will be uploaded, and I think it will be hosted on YouTube, and there will be some link on the Embedded System Week website. And if you don't find the link, just let me know. You can contact me, and then I will make sure that you have the link to the recording. Okay.
Thank you so much.
No problem. If there is any other question, we're here. Otherwise, thanks again for everyone, and especially the speakers that prepared a very nice program, and the attendees that have been listening to these very interesting insights. Thank you.
Thank you too. Bye-bye.
Thank you. Bye-bye. Have a nice weekend.
The same.